check, check. Okay, so let's get started. It's my great pleasure to introduce our distinguished speaker today, Professor Alexandra Silva. Professor Silva is a renowned theoretical computer scientist whose research has significantly increased our understanding on semantics of programming languages and modular development of algorithms for computational models. Professor Silva is currently a professor at Cornell University, and previously she held professorship at University College London. She has received several prestigious awards, including Roger Needham Award, Pressburger Award, Leverhulme Prize in Engineering, and a Royal Society Fellowship. Today, Professor Silva will talk about outcome logic. Please join me in welcoming Professor Silva.
Okay, thank you so much. Can people at the back of the room hear me okay? Is okay? Cool. So yeah, thanks for this invitation. It's a pleasure to be here, and I'm really glad I made it despite the snow and the cold and the overflow at the hotel last night and all of that. I'm glad to see the room packed and lots of people here. So what I want to do today, I want to talk about this project I've been doing for a few years with my student Noam Zilberstein and some collaborators on outcome logic. And I want to tell you about sort of the latest results. And I'm going to use a lot of examples trying to bring some intuition for the problem we've been trying to solve. This sort of program is a little bit like a tale as old as time. They're sort of the beast, which are programs, and programs can get quite complex and can have different sort of constructs, and I'm in particular, for those who know me, you know that I'm particularly interested in probabilistic programming, so programs that have access to sampling and random variables, and that can manipulate values based on that. And then on the side of the beauty, we sort of have formal methods, and for the purpose of this talk, I'm particularly interested in the beauty of logics. So how to use logics to sort of attack program analysis and program verification. And there's been a lot of work done on program logics, right? So what I'm going to tell you today is really not just my work, but it's sort of founded on a huge body of work. There's a paper that I did not reference later, but might be worth mentioning. There's a paper that Patrick wrote a couple of years at POPL' with a huge cube of program logics that I will be touching upon at points, but I forgot to add a reference to that paper. But that cube and also another thing I wanted to mention is a slide that Ilya Sergey has on his website on concurrent logics. And I think that slide has probably about 20 or 30 logics in it. It sort of shows that there's a huge space of work. And each of that work has a purpose. As a class of programs, they're tackling a class of properties. They focus on different aspects of how you can use a program logic, but they all come from this sort of idea that analyzing programs you should be able to specify it in a simple and intuitive way. So you should be able to write down a certain program. I use C for programs here for command. And you should be able to somehow write down specs that look a bit like this. If P holds before the program executes, then at the end Q holds. And this is a very powerful way to reason about programs, because depending on how you set up P, you might end up pruning the space of your program, and that might help you reason about more complex properties that you might otherwise not be able to because C is too complex. Okay, and this is what sometimes is referred to as the axiomatic view of program semantics and program analysis. And so this is, for the purpose of my talk, when I say program analysis, program verification, this is sort of what I mean. I want to build logics that look like this for certain classes of programs. Okay, and these triples or program logics in general have formed the basis of many analysis and verification tools. Many of you have heard probably talks about infer, which is this tool that uses separation logic inside Meta. There's Jillian, which is a tool developed at Imperial. And then I sort of separated them in two groups. There's this group of tools here on this side, which are more sort of on the theorem prover or proof assistant space. So we have the large project on Iris, on concurrent separation logics, and then Daphne and Coq and Lean and Viper. So there's sort of a wide range of tools that have implemented different forms of program logic to do program analysis. Okay? But what I'm interested to tell you a little bit about is this class of programs that I call probabilistic concurrent programs. And I want to sort of show you that up to this work we've recently done, there was not really a good way to analyze these programs using this sort of intuitive program logic approach that we have done for sequential programs, concurrent programs, probabilistic programs, but for the mix of them, nothing much was there. And what are these programs? Why am I wanting to mix probabilities and concurrency? So here's an example that's going to be my running example for the whole talk. And then I will tell you where this example sort of comes from, and more broadly where these programs occur. But let's start with an example so that we sort of get some terminology in place. So I have a language that has two things that might not be standard. One is I can sample from a distribution. And here in pink, I have this command, flip, which is basically just allowing me to flip a coin or to sample from a Bernoulli distribution. And I can store the result of such coin flip inside the program state, inside the program variable. And the other thing I have in this language is this operator parallel that allows me to execute basically programs in parallel. Okay? Now, if I give you a program like this, you might wonder, what does it do? And what questions may I want to ask about this program? So here's one question. Is Z, variable Z, a good source of randomness? So let's see how we build variable Z. So we have a few variables. We have y, x1, and x2. And basically, y is set to 0, and then later copied to x1. And x2 is coming from this coin flip. So x2 is clearly a good source of randomness because it comes from a coin flip, assuming this flip is implemented in some sensible way. And then z is just the XOR of these two variables, x1 and x2. Remember, x1 is definitely 0, or is it? Steve, are you awake? Do you want to help me with this program? Is is y definitely 0? Oh. Sorry. See, I was hoping Steve was going to help me with this example. Okay, I have.
You never said anything about the scheduler.
Okay, I never said anything about the scheduler. Someone is catching me on my explanation. So what can happen here is that indeed I have this parallel here as this y being set to 1. So if I don't tell you anything about the scheduler, when you get to z, you actually don't know if x1 is 0 or not, right? Because you start with y is 0, but at some point in the execution of the second program, you might have set y to 1, okay? So here's challenge number 1, right? When we have these concurrent programs, you have to worry about things like schedulers. But worse, I now have this probabilistic coin flips. And so I also have to worry about other things like correlations and how they interact. But let's focus on this particular program. What would it amount to say that Z is a good source of randomness? So if I would want to specify this in a program logic, in an imaginary program logic, which we don't have yet, this would look something like this, right? I mean, intuitively, I would want to say, without any assumptions, I would like to run C and be able to assert that variable Z is distributed according to a Bernoulli distribution of bias a half. So it's a fair coin flip, okay? So this is what I sort of would like to do. And so during this talk, what I want to sort of show you is what are the challenges and what are the sort of hurdles in designing a program logic to derive a triple like this for a program that has both coin flips and parallel ILIA?
You didn't say anything about the memory model. I assume the program on the previous slide doesn't have an undefined behavior.
Indeed, I haven't. That's another challenge that actually I'm not even going to touch upon my talk. But yes, there's also the issue of memory model. Indeed. Okay. So I promised you I would say at least a few words about why we care about these programs. Like, why are we just making up something, which we sometimes, I'm a theoretician, as Ashutosh said, and sometimes we do that. We create our own problems. We have probabilistic programs. We have concurrent programs. We put them together. Why not? But actually, these programs are interesting because they can be used to formalize correctness of certain randomized distributed algorithms. For people who are familiar with some of these this literature with a long tradition, for instance, the dining philosophers. Okay, that's an example of a randomized distributed algorithm for which, so far, we don't have a formalized proof of its correctness. Okay, and this would be really interesting because a lot of the papers on the randomized distributed algorithms have, of course, analysis of the algorithms that is more pen and paper and based on sort of expectation-based reasoning on why the algorithms are correct. So it would be really cool if we could formalize them in a language and have a program logic that you can mechanize and actually prove them correct or find bugs. I mean, these programs are quite subtle. These algorithms are quite subtle, and it would be interesting to sort of do that analysis. And then, less long tradition, but currently very hot. These probabilistic programs appear in a lot of AI and ML applications. And these days, with LLM architectures and whatnot, the use of parallel is also becoming really common. So that's another source of examples that one could find to formalize in this language. These programs are a good target for formal methods. As I just mentioned, program behavior is very subtle, and Ilya and Shira mentioned two things. Both the memory model and the scheduler are hard to reason about. And once you add these coin flips, then you have to worry about correlations between your variables and how these correlations actually interact with execution. And if you really want to be sure that your program does what it's supposed to be doing, then having some form of automated reasoning is essential. And just to sort of finish the trifecta, they are also a good target for program logics because the complexity of these algorithms, these randomized distributed algorithms, really demands that you have methods that are scalable. And program logics, one of the biggest sort of strengths is that they offer you this compositional reasoning. So this is sort of a good playground for program logics. Now let's go back to this running program. So this running program is, we call this an entropy creator because it's sort of creating this variable z. And why is it challenging to execute this program? I already hinted at some of the things here, but just to recap, if I write this program in a certain language, and I want to provide the language with some form of the notational or operational semantics, the first thing I need to understand is that a construct like x2 is assigned flip a half, asks that my semantics needs to be able to handle some form of probability distributions. And here I should say, for the people in the audience who are familiar with probabilistic programming, that in this language, I will eventually want to have loops. So even if I only allow Bernoulli distributions, I can then build all kinds of things from coin flips and while loops. So having just flip is not actually so simple as it might look at this point. Okay, so we have flip, and we need some sort of probability distribution in the semantics. Then we have this parallel, which because of the scheduler, or how we choose to encode the scheduler, will break compositionality of the semantics. Why is that? So as we put more threads in parallel, so let's imagine I start with the program here on the left of the parallel, right? And I give it some semantics. That semantics has to somehow take into account the fact that in an open world, if I put the other program in parallel, it's actually going to affect my semantics. So we have to be a little careful about capturing all these possible sort of interleavings that happen from scheduling other things in parallel. And this is what makes the semantics really sort of very interesting mathematically and very challenging. And then the last thing is that this is a very brittle programming language, or giving semantics to such programming language is very brittle, because minor changes to a program might really break your intuition on what's happening. So let me show you this by example. So I showed you this program before, and I sort of argued that, you know, I have my x2, which is sort of a high quality randomness. I have this assignment to x1, which is low quality because y is just a deterministic value. But, you know, I will show you at the very end of this talk that this value z is actually distributed according to a Bernoulli distribution. So it's a high quality randomness source. And so I will show you at the very end of my talk that this triple is valid for this program. But here's what happens if, for instance, we shift those first two things. So you see what I did here? So let me just go back for a second. So in the first program, the program I'm using as a running example, I first store y in x1, then I flip the coin, and then I calculate z. Now, in the second program, I first flip the coin, and then I assign variable y to x1. And so, same question, is z a good source of randomness? I mean, if you just squint at it, you might think, sure. I mean, nothing really has changed, has it? Yes, some people say yes. Who wants to okay.
The scheduler can, if the scheduler can see x2, then something has changed.
Okay, so the answer here in the front, if people didn't hear in the back, is that if the scheduler can see x2, then something has changed. So let's make this a little more concrete. So indeed, this will be a low-quality variable, randomness variable, and this triple will not be valid. And why is that? So if we write down the execution of this new program, here's what it looks like. I assign 0 to y, I flip my coin, and then based on whether x1, you know, whether my coin flip, whether my x2 is 1 or 0, I can do different things to the parallel thread. So indeed, as Shriram was saying, the scheduler can now force z to be 0. So think of this almost like an adversary, right? The scheduler is an adversary, and it's like playing against you. And if it has the information about the coin flip, then your XOR can be fully determined by what the scheduler does to that second thread. Okay? So I hope this example sort of gave you a glimpse of what is at play here. So we have these programs that can manipulate random variables and have these parallel threads that we need to care about. So we need to have some form of scheduler or some form of parallel execution. And we would like to reason about them using program logics. So here's what we would like. We would like to have this language have a compositional semantics. We would like to have some proof rules that are somewhat intuitive and that can handle this mix of effects, because you can think of probabilities and parallelism as a sort of an effect in the sense of a monad. And here, for those familiar with this old work of Varaka and others, handling a mix of effects when you have probabilities and non-determinism or probabilities and concurrency can very easily break the compositional semantics. So wanting these two things requires a little bit of care. And then the other thing we would like to have unbounded loops in the sort of programming language, and then later on also to have proof rules to reason about unbounded loops. Okay. Now, we've done some progress towards this, and I want to tell you a little bit about that. The first thing we did, and that's appearing at POPL on Thursday, we've sort of like ticked all these boxes, but for a restricted language. Namely, we replaced parallel just by a non-deterministic choice. So you can think of a non-deterministic choice as sort of a demonic semantics in the sense of an adversary, if you think that your adversary is playing against you. And so what did we do? We designed this language that looked exactly like the one I showed you in that program, but without the parallel, with a sort of non-deterministic choice. And we did a program semantics based on what we call, or what is called, convex power set. So let me spend a few words on this. The scheduler, so all the work we've been doing on this uses the notational semantics. And the reason why we went that way is that we want to sort of talk about the whole distribution that the program is manipulating, and not just sort of stepwise distributions. In order to do the notational semantics in a language where you have any form of non-determinism or parallel, you need to be able, your semantics need to be able to encode all these behaviors that may occur. They may not occur if the scheduler does not do it, but it could occur. And so your semantics needs to capture all possible executions that your program might see depending on the variables that you are manipulating. And so this convex power set disappears in sort of old work of Annabelle McIver and Carol Morgan, and someone else that I now blanked out. I apologize for, okay. Sorry, I blanked out the third name, so I apologize. But so the convex power set appears in this work back in the late 80s as a way to capture in a probabilistic language with a non-deterministic choice, which was somewhat restricted in their work, to capture all possible schedulers. So if you write a property, and so Annabelle and Carol have along the years worked a lot on expectation-based reasoning. So all their work is sort of targeted towards expectation-based reasoning. And what they wanted to capture there was basically this idea that for any scheduler you might choose, I can still prove this lower bound in my program. And so there they introduced this idea of using a convex power set to capture the semantics. And what we did in our work, we took that idea and we ran with it and proved that you can actually do unbounded loops. So you can basically compute fixed points. And again, I should give credit that a lot of these covering unbounded loops uses some old work on domain theory and work that goes back to Claire Jones and other students of Gordon Plotkin. There's a real rich line of work there that is finding, I think now, a lot of applications in this world of program logics. And so we sort of took bits and pieces of different works and put it together towards this language. And then we went on and designed a program logic that has rules for loops based on certain termination conditions. And there, thing you might have seen here on almost sure termination and so on plays a role to make sure that you can have sound reasoning around loops. And so details on this will appear on Thursday at POPL just after lunch. I encourage you to attend my students' talk then. It should be fun. Okay, and then from here, we wanted to basically drop the restricted bit. We wanted to go and do something that had concurrent work. And as it turns out, this was harder. Oh, sorry, I should have said. This is joint work with my student, Noam, but also with Joe Tassarotti and Dexter Cousin that appears at POPL. And so then we wanted to go and do something more general and do probabilistic concurrent outcome logic. And this is, again, joint work with Joe and my student Noam. And as it turns out, it took us a while to realize this, but just removing the restriction on just having non-determinism versus parallel, the convex power set was not enough. I mean, originally we thought that the convex power set would give us all we needed. And then slowly we realized that was not the case. And so we developed a new structure to give program semantics. And this I will give you details of in a moment. And we derived some rules. But as we did this new structure turned out to not exist in the literature. And so a lot of these domain questions about solving fixed point equations were not there. So we couldn't just take some old work and have loop and bounded loops. So in this work on probabilistic concurrent outcome logic, the language is the full language. It has a compositional semantics, but we only have bounded loops. So think like a for loop. That's the only thing we have. And so we thought a little more about it, and we now developed the domain theory for this new structure, which again, I will give you details in a second. So we did a whole paper on the domain theory of this new language, but we haven't gotten around doing the proof rules. So hopefully soon, I can tell you the full story. But today I can't, because we don't have. So we've only made it to the point where we have a full semantics on one side, we have a nice proof rules on the other side, but we don't have both together. So what I will do today, I will mostly show you examples from this draft, where we have these proof rules, but no unbounded loops. So the example I showed you was not using loops anyway, so I can show you the proof in that setting. So what I will do now for the rest of my talk, I will show you a little bit about this new structure to give the notational semantics to programs with concurrency and probabilities. I want to really spend about 10 minutes or so talking about the works we sort of got inspired in, and there's works also appearing at POPL this week that touch upon some of the things we've done. So I want to spend some time doing that and then show you some of the technical details of this new structure. So let me sort of talk a little bit about these many threads we were trying to bring together. So there's a lot of work on concurrent separation logic. I put Iris here, but really there's much more. From the very beginning, when CSL was invented, to all the many variants that have appeared in the literature, as I mentioned in my second slide, both Iris and Jillian and all kinds of other tools implement procedures for separation logic, for concurrent versions of separation logic. There's like a whole list of things. Probably this week at POPL, there are papers that touch upon these sort of CSL-like languages. In the last 5 years or so, there's also been a lot of work on probabilistic separation logics, starting with PSL back at POPL 2020, and more recently with Lilac, which is a beautiful framework that appeared at PLDI in 2023, and Bluebell, which I believe is appearing at POPL later this week. There's a lot of efforts in sort of reasoning about programs that manipulate random variables. And some of what I will show you here was particularly inspired by these three works, PSL, Bluebell, and Lilac, and the way they reason about independence of variables and conditional independence. And I really, again, one more plug for the POPL program. If you're here for the rest of the week, do attend the Bluebell talks. There's a lot of insights there on designing a language. Now, what we want to do is bring these two things together. And in order to bring these two things together, concurrent and probabilistic, we need to draw lessons from both, but we also need to be a little careful about how these things get combined, because easily you can break, for instance, compositionality of the semantics. So let me tell you about some things from this space that we drew on and that really played a role in the design of the language. So first thing is, from going back to the original design of CSL, here's one rule that is really crucial in concurrent separation logic. What does this rule say? It says, if I have two programs executing in parallel, I can independently analyze them, and then I can say something about the overall composition as long as I have separation. Okay? So this basically tells me, if my programs, for instance, are executing in different parts of the memory, and they don't interact, then I can do compositional analysis. Okay? So this is one point. Now, if C1 and C2 are not just regular imperative programs, but have probabilities, what does this mean? Okay? And this now goes to PSL, where the sort of key insight behind PSL is that separation can be interpreted as probabilistic independence. And sort of the beauty of PSL is that they drew up a model, which is really a model in the sense of the same model as in separation logic, is what is called a model of bunched implications, where they interpreted the separation as probabilistic independence. So for instance, here's an example. If I do 2 coin flips, x and y, so I do 2 coin flips and I store them in 2 variables, x and y, and here in the precondition, you see the star from separation logic, and what this is saying is basically just saying x is pointing to some memory, y is pointing to some memory, and they are separate, so it's not the same memory location. So if I have that in my precondition, then I can basically deduce that x and y are probabilistic, so are random variables distributed according to a Bernoulli distribution, and they are independent in the sense of probabilistic independence. Okay? And what is sort of neat about this probabilistic parallel rule is that it literally looks like the same as the CSL rule. It's just that the interpretation of this separation is now different. Okay? So that's one insight from PSL. Now going back to CSL. CSL has this rule where it says, okay, if you have shared state, because in that first example of CSL, I was talking about separating the state, but if you have shared state, you can still reason about parallel threads, but you now need to bring into play an invariant. Okay, so if you bring invariants into play, then you can still apply almost the same rule. So for instance, a program like this, where I assign 1 to z and then I execute these sampling instructions in parallel, I can still analyze because I can add an invariant to the rule that says z is in 0, 1. Or, you can even go further and say that z is in 1. Why not? But you can sort of like specify the value of z deterministically. Okay? And so, again, you can reason about shared state as long as you have invariants. Now, the problem with this is that, in this example here, z is 1 is a deterministic action. And if suddenly I allow randomized shared state, which in this new language in which I want to have coin flips and parallel sort of live together might happen, then we have a problem. So here's another example, sort of flipped in its head from the previous one, in which I flip the coin first, and then I do something with x and y in parallel. What can I say about x and y now? I mean, they're clearly not independent, sadly. But there's something here that I might still be able to say. Can anyone guess what I can say about x and y? Yes? Exactly. So they are not independent, but they are conditional independent on z. Okay? So in a world in which I have some form of shared state, and that shared state is randomized, I need to be able also to capture and reason about conditional independence. And this is something that, the work on Bluebell and Lilac and other works have beautifully captured on how you do it. And so what we did in our work is to observe that in order to reason about conditional independence and deal with parallel, you need to sort of break down the outcomes of the sampling operation. Okay, let's think for a second intuitively what this means. So when I say x and y are conditionally independent on z, it basically tells me I need to know z first in order to say something then about x and y, right? So intuitively, if I give you a list of finite values z can take, then you can prove one by one that x and y are independent. Now, of course, in a real probabilistic world, you don't have a finite number of values, but let's for a second imagine you do. That is what it boils down to. Once I give you the list of Z, you can prove probabilistic independence. And so what our work sort of exploits is exactly that idea, is that conditioning boils down to breaking down the outcomes of the sampling operation. And so what we've done in our work is every time we can prove something about Z of the kind Z becomes a Bernoulli a half, then that expands to this thing here. That looks funny, and I will explain in a second what it means, but intuitively it just says my Z, my variable Z, and so note that there's a capital Z and a non-capital Z. So the capital Z is a meta variable, and the little z is the real program variable. And what this is saying, this is a program logic construct that says, create a meta variable that is distributed according to Bernoulli a half, but you could put anything there, and assign it to Z, and take a big outcome conjunction. So you can think of that big O plus as sort of a conjunction of all possible values I can give this meta variable. And with this in mind, that's how we can expand. That's how we design the logic. And so the key ingredients in our logic are basically separation, in the sense of separation logic, but now interpreted in this probabilistic world of independence, and the fact that we have this outcome conjunction. And this outcome conjunction allows you to talk about how to break down a distribution in smaller pieces. Okay? And then, of course, the devil is in the details and the semantics, which I will tell you in a little bit more details about. But really, if you take something from my talk, is this slide, is that you can marry separation in a probabilistic world, a la PSL, Lilac, etc., all these logics, with a way to break down the effects of the parallel in the distribution. And that comes from the outcome conjunction. So outcomes, and this connective is something that appeared originally in our work on outcome logic, where we were trying to unify correctness and incorrectness. So this was in a non-probabilistic setting. But we later instantiated to a probabilistic setting. And here is really, I think, the key insight about this connective as a logical connective, is that for many probability and for many analysis of probabilistic programs, you need to get your hands on the entire distribution. It is not enough to know what you do on one trace of your program. Especially if you're trying to build semantics of loops, you need to know what is the entire distribution your program is computing. And so in the probabilistic setting, this O plus basically enables us to reason about the entire distribution and break it down in compositional pieces. And for probabilistic concurrency, sort of the key insight was that these outcomes can be made effectful in the sense that they can be instantiated for different monadic effects, and they can be composed if you're careful enough. Okay? So this is sort of where this is coming from. But let me go back a little bit to the devil, to the semantics. And let's just look at, let me put these three things on. Let's look at the three components of the language, right? Of the language that we're trying to build and the semantics. So there's a component that comes from probability. And if you look at the work on probabilistic languages going back to the 80s, to the work of Kozan and others, there's the use of Markov kernels and convex spaces, convex algebras to give semantics to pure probabilistic programs. In concurrency, there's many ways of giving semantics to a concurrent program, but some classic ways would be using POM sets, event structures, and you're sort of trying to capture, to abstract away the scheduler through these algebraic structures. Now, in our case, we also want to have control flow structures. We want to have if-then else's, while loops, and we want those to, to be able to use tests that are Boolean, but also probabilistic. And we want to combine these three things. So when it comes to just programs with control flow, I mean, there's also structures, very old structures, using Boolean algebra and control flow graphs. And really what we were trying to do is mix these three together. Now, the mix of concurrency and control flow just on its own is already quite brittle, in the sense that if you're not careful, your variables might be changed between, your Boolean variables might be changed by parallel threads, and your interpretation of if then else might break. But now we're trying to put all these three together, right? So this is sort of where we are. And we couldn't find anything in the literature that would enable us to capture semantics of this. So we came up with a new structure, which we call POM set with formulae. So POM set is the branching structure that captures the concurrency. The formulae are formulae that will capture the control flow. And then the nodes of the POM set are going to hide the probabilistic actions that will only be instantiated when you need them for the program logic. Okay? So this POM set with formulae are a new structure, and here's one example. For instance, if I have a program, an if-then-else, so here's a sort of nested if-then-else, this would be what the semantics would look like. And here A1, A2, A3 could be probabilistic programs. So the POM set will basically have two types of branching. So this is sort of the difference with the usual POM set semantics. Certain nodes, like for instance, Y1 and Y2, correspond to the branching of the first if. Okay, so the node X is at a point. So imagine in some program execution, I get to X, and I'm at the beginning of executing this if-then-else. So at that point, I branch, and I record in my formulae that I branched. And I branched using X. So the formula for Y1 is X, and the formula for Y2 is not X. And then when I do the second if-then-else, I accumulate the tests I've made so far. So what this formulae gives us is a source of how I got here. Okay, so basically, if at some point I unpack inside Z1 what probability distribution I have in there, I can tell you exactly what choices you made in your control flow program to get there. And this, as it turns out, is key to get a compositional semantics. Because if you don't have this source of control flow, then you might be interleaving threads you shouldn't be interleaving. And this is sort of where the idea comes for this. And so we have this POM set with formulae. And then at some point in our analysis, and I don't have time to show that, we are going to linearize this in the same sense, as linearization happens in concurrent separation logic. But in that linearization, the fact that each action is probabilistic is going to be taken into account. And so the probability distributions are going to be built compositionally as you do the linearization process. And so when you're done with your linearization process, you have a state transformer that tells you for every program state that you begin with, what is the probability distribution of output states that you end up with. And that sort of abstracts away the scheduler. Okay, okay. And so this is the language we gave semantics to, where the program actions are probabilistic, and the language semantics is a function from commands to this POM set with formulae. And there's, of course, for each program operation, we had to come up with suitable POM set operations that capture the right semantics. So for instance, for if then else, this POM set with formulae come equipped with this guard operation that basically annotates the formulas in the right place. And the fixed point, so the fact that the while loop is a list fixed point, this is where the work is in developing this new structure, because you basically need to show that this POM set with formula form a DCPO and that you can compute fixed points and so on. And that's where the technical sort of meat is. And so that is available in one of our archive drafts on this. Okay, I would like to spend the last, I know I'm running out of time, but I would like to spend the last few minutes just giving you a glimpse of the logic. So these are the probabilistic assertions. There's our sort of outcome conjunction that says I can sample from a distribution and do a conjunction of formulas. From these, and so the rules I'm about to show you do not include unbounded loops. So this is like without the loops for a second. For these type of assertions, we came up with rules for all the program commands, including a bounded loop, so a for. But let me just zoom in. This is, of course, I don't expect you to read this. Let me just zoom in on one of them. This is a simplified version of the sampling rule. And the sampling rule says, so this is a, sort of a simplified version that says, if I'm sampling from a distribution D, and I'm storing this in a valid pointer, meaning that this pointer exists, then I can conclude at the end that my variable is indeed follows this distribution D, okay? Now with this in mind, or with this sort of set of rules, we can go back to our example, and we can actually prove that our variable Z built with this XOR from a low randomness source and a high randomness source ends up being a good source of randomness. So the proof has two steps, basically. The first step is to show that if I keep my assignment x1 in the beginning, because I told you that if you swap it, then you run into trouble. But if you keep your assignment there, then what do I want to know about x1 that will be useful in my proof later? I want to know that x1 does not leak information, meaning that, at that point, x1 is there, but I cannot use the information from x2 to set anything, okay? So here is, so you can focus just on the last line that says, if my y, my variable y, so this is an invariant, if my variable y is Boolean, meaning, it was 0 when I set it, but I don't know if my scheduler has changed it, so my invariant has to basically consider both options, that could be 0 or 1. Then the assignment of x1 becomes y. Also, the only thing I can say is that my x1 is either 0 or 1. Okay? So there's nothing here. Basically, I didn't learn anything new in some sense, but that's good news. So I can prove, using the rules I showed you before, you can ignore the proof, but I can prove that the assignment of x1 is y, only knows that y exists and is a Boolean variable. Okay? With this triple at hand, you can then use that triple and the sampling rule to go further and show that the value of z is indeed a fair coin. So how does this work? I basically, I start with the triple I want, and this is a very sort of classic program logic proof. I start with the triple I want, and then I apply the rules, the structural rules that the program structure tells me to. In particular, I have to apply the sequencing rule that will allow me to break the sampling from x2 and the sort of the building block for z being XOR. And so you end up proving that, so here on this side, you end up proving that if x2 is a Bernoulli sampling, then x2 is indeed, you can deduce that x2 is distributed as a Bernoulli variable. And that's a simple application of the sampling rule. And then on this side here, I didn't have space on the slide to put the rest of the proof. But on this side here, you use part of what we proved with this triple to basically then combine in the sequencing rule that the XOR takes the value from x1, which I know is either 0 or 1, and takes a value from x2, which is this Bernoulli distributed variable, and ends up building this new variable that is indeed a Bernoulli distribution. So I don't expect you to read this slide. I just wanted to sort of put on one slide the proof. Yes?
So, yeah, it's very nice. I was just curious, what will this proof break if you sort of flip the order of the two assignments?
So in this star here, which I haven't shown you, you wouldn't be able to basically use the x1 as in 0, 1. Yeah. Yeah, so that, yeah, you just made me realize that should have been my next slide, which I didn't put. Yes. Okay, I'm coming to the end of my time. So I'll just conclude here and take questions. I hope I gave you a glimpse on why these probabilistic concurrent programs are an interesting class to look at. I mean, randomized distributed sort of algorithms and systems have been studied for a long time, but there's a lack of formalization in that world. And I think we, as the verification and semantics community, have a good playground there to actually contribute. With all these advances we've seen in program logics in the last 5-6 years on probabilistic and concurrent analysis, I think this is a great time to be looking at this. As I said, the work on Lilac and Bluebell and PSL and outcome logic, there's a flurry of really interesting things coming out at the moment for programs with probabilistic variables. So it's a really exciting time to actually try to tackle this class of programs. It's a good playground for us as formal methods people because these interactions between randomization and concurrency are really subtle. So it's very easy to make a mistake in a pen and paper proof, really easy. And so having formal models and program logics ensure correctness, compositionality is a big thing, and I think we'll see a lot of interesting work coming out. And so our work focused on sort of the denotational model, but I'm sure that there's other approaches using operational semantics and other things. But our work has basically focused on this idea that you can have a denotational model that enables you full reasoning over the distributions and how to derive a program logic from there. So this is work in progress. More is on the way, and a little bit of advertisement. This is the main work of my student, Noam Zilberstein, who will be coming up on the market next year. Go and see his talk at POPL this week. He's doing a lot of cool work, and I think this is nice work, and I hope you enjoyed the little glimpse I gave you from the work. Thank you. Ilya.
Thank you. That was a very nice talk. So I'm still thinking about the initial example that you've shown with the adversarial scheduler, that when you swap the two statements, check out the value and chooses the one that you don't want to. So it seems like your reasoning principles are geared towards this adversarial scheduler, but I would imagine in reality, most of the schedulers don't have this power, so they would give you like something close to like uniform distribution of picking one step of each thread, or maybe something like slightly biased, but like without access to the state. So would you be able to encode all this spectrum?
Yeah, so that's an excellent point. So indeed, we are at this extreme. So we are developing our work at the extreme of the adversarial scheduler. You are right that it would be really interesting to have a shade and that you could control how adversarial your scheduler might be. What we've done so far, you can't. But for instance, in this convex power set world of the work of Annabelle and others, they have looked at variants on the convex power set that represents different types of schedulers. So I would imagine, and I don't want to say that it's easy, but I would imagine that one could draw some inspiration from there and bring it here. But yes, that is definitely not something we've tried yet. But it's a very interesting point. Thanks, Ilya.
Thank you so much. I was just wondering with the POM sets, I may be misunderstanding it, but does that suffer from state space explosion in practical applications?
Yes, in the sense that, well, yes and no. So yes, if you do it naively, you're going to end up with a huge structure. No, in the sense that you can reason symbolically, so you don't need to build a whole POM set. And if you reason symbolically, then you can tackle the state space explosion. That's not something we have done so far, but that is something that has been done in concurrent work, and I would expect that transfers here as well. But yes, that is indeed like the downside of a lot of the denotational semantics for concurrency, is that you're trying to capture the whole behavior. And when you do that, there's no running away from the fact that you need to encode the whole structure. Yeah. Oh, sorry.
There are two things I have not really understood. One is you don't seem to have synchronization primitives. And second is, if the scheduler follows a random law, and you have random choices in all processes, I don't understand how the output can be independent of the distribution used by the scheduler.
Okay, so that is indeed an assumption we made. So our scheduler is not randomized. Our scheduler is a regular sort of non-deterministic scheduler. And sorry, what was the first? You asked something else. Oh, synchronization primitives. We don't have synchronization primitives so far, right? So that's something we're actually thinking about right now, is how to add some form of synchronization. But so far, it's a really plain language that if you put a parallel in, you're sort of thinking in the back of your mind, you're going to do all interleavings.
All parallelism logic.
Yes, yes. So it is in that sense maybe I mean, it is a first step towards something, but I agree that might not be the most realistic step. It is enough, though, for the dynamic philosophers, it is enough. So for some things, it is enough. Yeah. Oded.
Thanks. I guess to follow up a little bit on Ilya's question, this adversarial scheduler that can see into the variables you've sampled so far, I don't know, maybe it feels a little weird for concurrency, but it has it feels like in many cryptographic protocols and kind of zero knowledge proofs, that's the kind of adversary that people are considering. I was wondering if you think that can be applied to analyzing these sort of protocols.
Yeah. So in the original PSL work, they already sort of exploited some of these cryptographic protocols. We haven't spent much time looking at versions where the parallel would make a difference. So all the examples we can do so far, they sort of were already covered by the PSL work, or the follow-up work on conditional independence in any case. But yes, it is a good point that making this adversarial assumption is something that in the more security world might make more sense. And some of the randomized distributed algorithms we've been looking at, this assumption is made. So yeah, thanks.
So my question is about the way you write your specifications. So these are in sort of standard pre-post condition form.
Yeah.
So I was wondering if you extend to omega regular, temporal logic, infinite computations, would the same sort of theoretical foundations that you're putting down, would those still work, or are there special challenges that you?
So I didn't have time to show this, but in this work on unbounded loops, we actually have to take into account infinite traces because, as it turns out, for some of this probabilistic reasoning, finite traces are just a bad approximation, so the probabilities you get are just incorrect. And so there, we do talk about infinite traces, but not in the sense, so the logical connectives still don't talk about omega regular, but the traces we consider are infinite. Yeah.
So, but the specifications are still...
They are still like this, yes. It would be interesting to see if one could use omega regular languages, yeah, sure.
So one of you showed two examples. In one, you could prove a Ho triple, but in the other, your proof failed. But I'm wondering if there is something by the way of a counterexample or a demonstration that could actually show the information leak.
Yes. Okay, so we haven't done that yet, but that is something that's very close to my heart. Sort of this counterexample generation, like what I envisage, but again, we haven't done it, is having some sort of bi-simulation construction proof that fails. And if you do it in a stepwise fashion, but then we would need also some form of operational semantics, you can actually trace back where it failed. And that is something I would really, really like to do, but we haven't done so far. But yes, you're right. Like the fact that our proof fails still doesn't tell us that some other proof method might not work. What we really need is actually a counterexample generation method. Yeah. Cool.
I have the impression that in this talk you make a bounded non-determinism hypothesis. Is
Yes,
it true?
correct,
Okay.
correct. We make all kinds of bounded assumptions, yes.
That's disappointing for me.
No, but Patrick, we have solved that part in the next paper, in the notational. So we're working.
The other talk.
You have to choose. We're working on it, one step at a time. Okay.
Okay, that's the time we have. Let's thank Professor Silva again.
Thank you.
you. Here. Yep.
Okay.
Seems like it is.
Okay, yes, it is there now.
Okay. Hi. So audible? Yep. Okay, I'm
Is there here the speaker of the second talk? Yeah, do you want to try before, just 1 minute before starting? Okay, so let's start this second session of the conference. So, okay, the first speaker is Daisuke Ifi, and he will talk about a real blasting extension of CVC5 for reasoning about floating point arithmetic. So,
Okay, thank you for the introduction. So, my name is Daisuke Ishii, and this. Maybe I should stand here. So, this is a presentation of a tool paper about an extension of CBC5, an SMT solver, for reasoning about floating point arithmetic. So first of all, let me give you a brief overview of floating point arithmetic. FPA, in short, enables reasoning about numerical systems by SMT solvers. So here we have a simple formula in FPA, which involves variable x of the sort of 8-bit FP numbers. And so SMT-lib also provides the floating point theory so that you can describe like this as well. And when solving this kind of problem with SMT solvers, the standard technique, a standard approach is bit bursting. So with this bit bursting approach, we prepare bit vectors for the variables and the constants in the formula, and also encodes a circuit for the basic FPA operations. And roughly speaking, the problem is translated into an instance of the propositional subprogram. Okay, so at present, an issue with the bit bursting approach is scalability. So, for instance, if we modify the sort of variable x here into the sort of 64-bit FP numbers, then obviously the number of encoded bits will increase accordingly, so that results in a large SAT instance. And on the other hand, SMT solvers are good at handling real arithmetic formulas. So, for example, if we can somehow have an approximated formula for the original formula, like this one, then sometimes we can solve the formula very quickly. So based on the observation like this, here comes the idea of this real bursting approach. So this real bursting approach, it means to solve FPA problems in real integer arithmetic, assuming axiomatization of FPA. Actually, the name real bursting is put by me following the following bit bursting and int bursting, which was proposed recently. But the idea is not new. There exists studies on the same approach. But anyway, with this approach, we prepare an axiomatization of FPA in extended real arithmetic, like this one. So this example is on the multiplication operator. So for example, an axiom here describes the finite case of the operation. So with some conditioning here, it is saying that the value of the operator should be the rounded value of the mathematical product. And the axiom here is for the case of having -0, and so on. So this real bursting approach solves FPA problems in RRA, assuming the axiomatization like this. But the key point here is lazy manner of instantiating the axioms. So in practice, it is efficient to have firstly having an abstracted formula like this one, where the multiplication term is represented by a fresh variable. And here and here, we have placeholders for putting some additional constraints. So, for example, here, this placeholder is representing the subset of axiom instances that characterizes the value for the variable here. So there exists tools implementing the approach, but according to the preliminary experiments, the performance is quite limited, maybe due to the prototype status of the tools. So the main question of this research is how far can we go by optimizing the implementation for the real bursting approach? So here are contributions of this research. First, we propose a new axiomatization of FPA. And then I have built a practical implementation within CBC5 SMP solver. So it was implemented as an alternative FPS theory solver. So CBC5 has a default bit bursting solver. So my extension can be used as a kind of an option to it. And then using the tool, I have made experiments to evaluate the performance. And I somehow confirmed that our solver outperformed the bit bursting solvers for some practical bounded model checking instances. So I will come back to this in the later part. So let me explain some details. Okay, so first about floating point numbers. So they are numerals represented by epsilon number of exponent bits and sigma significant bits. But I just skip the details. But here I assume floating point numbers following the standard. So we could consider a set of 8-bit FP numbers and set of doubles, which has where epsilon is 11 and sigma is 53. Okay, so the elements of the set like this can be classified into several sorts. So first, we have the normal and subnormal numbers that can be mapped onto the real number line like this. So normal numbers can be placed on the blue region, and subnormal numbers can be placed around zeros. So by the way, we have 2 zeros. Some rationals are represented as FP numbers, so that, but other real numbers should have rounding errors. And so this plot shows how the errors distribute due to the design of this number system. And additionally, we have special values, namely positive infinity and negative infinity, and the not a number symbol. So what I propose in this research is a mapping like this from FP numbers to rationals. So what I did is easy, kind of easy. I just put special numbers outside the bound of normal numbers. And since we have 2 zeros, positive 0 is mapped to real 0. And minus 0 is just put next to the positive 0. But what's to be careful is that the special values are set properly so that they cannot be obtained by any FP operations. Then, based on this mapping, we can interpret FPA operators in RIA. So for instance, rounding operator can be interpreted like this as a function of this sort, and multiplication can be interpreted like this. And then on this interpreted function, we can describe a set of axioms. So for the rounding operator, for example, we can describe an axiom characterizing the idempotency of the operator, and the relative round error bounds can be characterized like this, and so on. And for the multiplication operator, so this was shown in the beginning. So the finite case and the minus 0 case can be described like this. So let me briefly explain the process with the tool. So first, as an example, we can let me consider this example. Then first, the tool translates the FPA formula into RIA. And in the beginning, in this case, is finite is expanded with its definition. And for FPA operators, usually they are initially translated into a purification variable. And this one is also somehow translated into a rational literal, like this. And then here we have 2 placeholders. And here we have a constraint for the variable, unbounded variable here, x, for having only the FP number assignments. And here we have, we put axiom instances for the multiplication term here. So, but we aim to detail this part gradually to be efficient. Okay, so so this is a basic process, following basic process. So first, basically, we let the SMT solver to enumerate models for this interpreted formula. And then we check the consistency with the original formula. So for example, if we have a model like this, which represents an assignment like this, then we check whether it is okay by evaluating the concrete term, each of the concrete terms. So for instance, the condition for the variable x is okay, and we evaluate we simplify the multiplication term so that we can check that it is equivalent to the constant. And in the same way, likewise, we can check for the given inconsistent model. We can also check it in the same way. So this process is done by this rewrite function of the tool. And in the middle of the solving process, two approaches for the axiom instantiation is used. So we have this eager run method and the lazy run method. And the eager run is basically instantiate in the initial phase. So for each of the FPA term, a general definition like this is instantiated in the solving context. And for lazy run tries to instantiate an axiom in a lazy manner. So a typical well-known method to doing this is in SMT solvers is this e-matching with triggers mechanism used for the universally quantified constraints. But here we use a different method, which is called model-based refinement. So let me just show you an example. So for the example of this multiplication term, so assume initially we try to solve with no axioms instantiated. So we may have an inconsistent model, some inconsistent model. Then we try, this lazy run tries to refine the model based on this model-based refinement mechanism. So here, it somehow instantiates this axiom in this form. And this is done because the initial, current model here does not satisfy this instantiated axiom. So with this mechanism, we can efficiently instantiate during the solving process. Okay, so this process is implemented as an extension to CBC5. Okay, so our implementation is based on the CBC5 theory solver extension mechanism, so which supports this model-based refinement mechanism. So what I have explained so far, these three subroutines are easily implemented using this architecture of CBC5. Okay, so in the rest of the talk, I would like to report some experimental results. So to answer these questions. So first one is about the correctness of the method and the implementation. And second and third are about the performance of the tool. So in the experiment, we have prepared 3 sets of benchmark instances. So first one is modified Winter-Steiger benchmark. So the Winter-Steiger benchmark is a major benchmark used for a kind of regression testing in this domain. So it contains many basic test cases like this one. So I have somehow modified each of them to make them abstract, because in the aim of stressing our solvers. And the second benchmark is the Gritcho benchmark, which is also a major benchmark in this domain to stress bit bursting solvers. And third one is prepared by me, which is an encoding of encoded formulas for the bounded model checking of simple reactive systems. Okay, and for the encoding, I have used these 3, either of these 3 precisions. Okay, so in the experiment, experiment was done with these 5 solvers. So I have somehow prepared 2 solvers with our solver with different tunings, and other 3 are state-of-the-art FPA solvers. I mean, bit bursting solvers. And this is a result for the 2 benchmarks. So for the first one, it resulted that our solvers had around 15% of unknowns and timeouts. I will explain why later. And for the Gritcho benchmark, so the state-of-the-art solvers are quite performed well. But for our solvers, we found that when solvable, our solvers was first. And this is for the bounded model checking experiment. So here and here, we could have best results among the solvers for some systems. And so maybe so this was expected, but we had the better scalability regarding the precision. Okay, so let me describe some discussions. So for the first question, we had no unsound results, so we consider the method and the implementation is correct. And for the second question, is our solver more efficient and scalable than existing solvers? So the answer is yes and no. So for some instances, we consider involving large numbers of arithmetic operators and also involving high precision FP numbers. Then our solvers performed well. And also, when the time limit is short, maybe our solvers can be better. And also, so this is kind of about the preliminary experiment. We also compared with existing real bursting solvers, and we confirmed that our solvers improved the performance a lot. And but for many instances, bit bursting solvers are still better. So maybe our solvers resulted in a number of axiom instantiations, so that the solving context becomes large, and it was inefficient. And also, for the first experiment with Winter-Steiger benchmark, we found that according to my investigation, we had some corner case situations where, so I consider currently we are lacking some corner case axioms so that we could not solve successfully. And for the third question, we could compare lazy run method and eager run method. And according to the experimental result, lazy run was more efficient for many instances, but there are also cases where eager run was better. Okay, so let me conclude. So I have presented an approach to regard FPA formulas as RIA formulas, and we have implemented the real blasting approach by using the extension mechanism of CBC5. And in the experiment, we confirmed the better performance than existing solvers on some practical BMC instances. Okay, I think that's all. Thank you for listening.
You said that your approach is better sometimes, but not always. But have you characterized in some way in which cases your approach is more efficient or scalable, and while in which conditions you lose scalability and or efficiency?
So basically, currently our solvers easily resulted in a situation like this one I described here, where a lot of axiom instances are generated so that the context becomes too large, so that it's just kind of stuck in that situation. But if it is successful, it seems to be efficient. So, yeah, but the classification of the two cases, I have not yet done. So, yeah, I could not describe a clear observation here.
Is there any other question?
So, as I see it, you are taking a formula in linear real arithmetic and translating it to real integer arithmetic. Is that?
No, we are using nonlinear arithmetic solvers.
Okay. So if your formula is actually a linear real arithmetic formula, would it still remain linear after you do this, or is there a way to keep it inside the linear real arithmetic fragment by real blasting, or?
No, I haven't tried that. I think even if the original formula seems to be linear, we can have some nonlinear terms.
So the reason I'm asking is in linear real arithmetic is very useful and very fast generally if you don't have the floating point, right? But then if you do multiplication of like known floating point numbers, right? So when you do linear real arithmetic, typically one of the floating point multiplication, one of the numbers will be known, right? So I'm just wondering if something special can be done if I know I'm multiplying it by 5 or 2.7 or 3.2, right? If one of the multiplicand is known, whether the translation can be improved. Maybe that's my question.
Yeah, I think that can be possible in some way. So actually, nonlinear solvers in CBC5 itself is also an extended solver. So basically, it's at the bottom there is a linear solver. So yeah, maybe if we, yeah, so I mean, on the side of nonlinear solver of CBC5, we can do something to be efficient, I think.
Okay, so let's thank the speaker again.
Thank you.
So next talk is about formally verifiable generated ASN, ACN encoders and decoders, a case study. And Samuel Chessou will be the speaker.
Okay, thank you for your introduction. And so I will present to you our work on the formal verification of serializers and deserializer in the context of space exploration. So to introduce our project, the motivation was that space exploration needs serializers because, of course, a spacecraft needs to communicate both with the ground and sometimes with other spacecraft, and data need to be serialized. However, writing by hand this kind of code is bug-prone and really hard and time-consuming. And as an example, I can give you the fact that the Solar Orbiter probe, which is currently around the Sun, had bugs in the serialization work. Different instruments were using different NDNS and different paddings, and so this had to be patched after the launch. And happily, this doesn't have an impact on the mission, but it's not always the case, and so correctness is critical because bugs could lead to either the loss of very important data or worse, of the entire spacecraft. And so one of the solutions is to generate the code to reduce this kind of problems. And so to do so, we can rely on formats such as ASN1. So what is ASN1? So ASN1 stands for Abstract Syntax Notation 1, and it's a language to describe data structures for serialization. Closely related to ASN1, we have a bunch of encodings that are describing how this data should be encoded at the binary level. So we have a bunch of them. And I will focus on ACN, which is a bit different because it allows the user to customize the binary encoding format. And this is particularly useful if you want to re-implement serializers for legacy formats, because you can customize to support this legacy format. Today, ASN1 is widely used in telecommunications, notably for HTTPS certificates and in 5G protocols. And for ESA missions, they are using the ASN1 SCC compiler, which is a compiler that takes a description in ASN1 and generates the code for both encoding and decoding these messages. So now let me show you an example of an ASN1 format. So here we have a message that is a sequence. So a sequence in the ASN1 language is a record type. And so here we have an ID, which is of the type that is defined above. So we have integers with it bounds for the flag as well. For the value, we have a real, which is a floating point number. And for the description, it's a string of 10 bytes. And so with this format, you can now add an ACN description that looks like this. And this description is actually explaining how the encoding should be performed. So here, for example, for the identifier type, which was an integer between the two bounds to be a 16-bit integer, we can specify the size in bits. We can specify that we want to use two's complement, and that you want to use little NDNS. And then for the message, let's say that we want to specify the flag, which, let me remind you, was between 1 and 255, should be encoded on 9 bits for legacy reason, that we want to use the positive integer encoding, and that we want this to be aligned at the next 32 bits. And for the floating point number, you can specify the IEEE norm like this. Okay, and now I will give you a background on the ASN1 SCC, which is this compiler used by ESA missions. So it's a compiler for ASN1 and ACN. Before our project, it was supporting C and ADA as backend. And the code that is generated is a combination of static primitives. Among them, we have a data structure, which is the bit stream, representing a bit stream. And we have basic encoders and decoders for the basic types, which are named codecs. And we have one codec per binary encoding. And it provides the building blocks for this generated code. And so our project was to add a verified Scala backend to this compiler. And so as we were performing formal verification, I will quickly give you an introduction on our tool that is called Stainless. So Stainless is a verification framework for Scala that we are developing in our lab at EPFL. And so let me start with an example of a proof. So let's take this zip implementation in Scala that takes a list of integers and a list of booleans and create the list of pairs recursively by zipping the content. And so now let's say we want to add some specification. So we can add a post condition like this using ensuring. So ensuring is part of the Scala language, but in the original Scala, it's performing a runtime check. And here we are repurposing it for static verification. So this post condition is saying that taking the first element of each pair is actually giving you back the first list you receive as argument. And if you pass that to Stainless, we get this counterexample. And indeed, this post condition is violated if the first list is shorter than the second list. And so to counteract this, we can add a precondition using require, which is also a static check, runtime check in Scala. And now if you pass this to Stainless, it's able to prove the post condition correctness and other properties such as termination. And so now let me give you an overview about how Stainless works. So it starts with the source code and then uses the front end of the Scala compiler to get the abstract syntax tree. And then it extracts its own version of the AST from this .AST, which is the one given by the compiler. And then it's applying a bunch of tree transformation on this AST, which could both reject some programs that are unsupported or transform away some features. So for example, here we are transforming while loops into tail recursion. We are transforming imperative code into functional code. And we are also rejecting some programs that uses aliasing in a way that is not supported. Then this AST is passed to the verification condition generator. It's based on the type checking of system FR, which is a type system based on system F with refinement types. And this type checking will produce a bunch of proof obligations that are then passed to Inox, which is a subsystem of Stainless that solves this condition on the Inox AST, which is a purely functional programs with higher order functions and different things like algebraic data types. And Inox is using SMT solvers and function unrolling to deal with recursion. And so function unrolling allows it to not use quantifiers in the SMT queries unless the user is specifying them. And it's better for performance and to find a counterexample like I showed you in the previous slide. OK, so now we can dive into this particular project. So I will present to you the verification approach that we followed. So we split the verification in two main steps. The first step was to prove the runtime safety of the code. And this includes the absence of crashes and the termination. If you want to have a look at the paper, this corresponds to levels 1, 2, and 3. At that stage, we had to make sure that the code was accepted by Stainless because Stainless accepts only a subset of Scala. And so we had to refactor the code to make sure that this was accepted. Then Stainless generates a bunch of VCs automatically. And this includes the termination, the check for the inbound accesses to arrays, the absence of overflows, the absence of division by 0, and so on. And so at that stage, we wanted to make all these automatically generated verification conditions correct. And in particular, for the inbound accesses, we had to add specification to all functions to express how many bits they would write or read to make sure that we could prove that we stay within the bounds of the arrays. And then the step 2 was the semantic correctness. And in this project, we were interested in the invertibility property. And so we did that twice, once for the static primitives and once for the generated code. And this is what we will explore now. And so we'll start with the static primitives. So we will talk about the bitstream and the codec for the ACN format. So starting with the bitstream, so as the name suggests, it's a data structure to represent a stream of bits. And it's used for both encoding and decoding. It is implemented on a mutable array of bytes with a moving cursor that is represented by two variables, one to point to the current byte and one to point to the current bit. It offers plenty of operations to read and write, both at the bit and the byte level. And this is the entire list, so I won't go into much detail here, but you can have a look in the paper. But for example, we have very simple functions like append bit and read bit that are used to write and read one bit at a time. But we also have more complicated functions like this append bits MSB first that takes an array of bytes and write a given number of bits starting with the MSB. So for the verification, the step 0 was, of course, to implement this scalar version of the bit stream. And to do so, we translated it back from the C backend. And we wrote a bunch of test suites to make sure that this implementation was behaving in a similar way. Then the step 1, as I said, was proving the runtime safety. And so we did the refactoring. And to prove the inbound accesses, we added the specification for the number of bits written and read by each function. And let's have a look at an example. So this is the append-bit MSB first. So for now, we will ignore the implementation, and we'll focus on the post condition. So here I omitted most of it, but I want to show you this particular one about the number of bits written. And so here you can see that we are comparing the bit index that we had before with the bit index that we have after. So the bit index is an index at a bit level computed out of the cursor. And here we want to prove that this bit index after is equals to the bit index we had before plus the number of bits we were supposed to write. And this proves that we indeed wrote n bits into the bit stream. And so we did that for all the functions. And then we could go into the step 2 of verification to prove the semantic correctness. So again, we wanted to prove the invertibility. That is, if you decode right after encoding something, you should get the same value back. So again, let's have a look at this example of append-bit MSB first. So now we can quickly see the implementation. So it takes an array of bytes, a number of bits to write, and a from, which is the index to which we should start in this source buffer. And it is implemented in a loop that is here implemented as a tail recursive function that writes bit by bit, taking from the input array and writing to the bit stream. And the post condition here, again, I omitted part of it. So the line 4 is constructing a new bit stream instance based on the one we have after the call by just moving the cursor back to where it was before. And then we would read n bits from this new bit stream. So we would actually read the bits that we just wrote. And then we are comparing them with the input buffer that we received. And so here, please note that the read bits function returns an array of bytes, again, to represent the bits that we are reading. And this is important for the next step. So now let's discuss quickly the proof of this function. So it is done by induction. And so as I said, we are writing bit by bit into the bit stream. And so your induction hypothesis is that when you are writing bit I, you can assume that from bit I plus 1 to the end, this is invertible, and you have to prove your step for the bit I. But as the read function is returning an array of bytes, this makes applying this induction hypothesis tricky because reading from bit I plus 1 returns a completely different array because everything is shifted by 1. And so this makes applying this induction hypothesis tricky. This was not an issue for the safety because we did not prove anything about the contents, but only about the number of bits. And so the solution we found was to go through a list of bits. And so we re-implemented a read bit function that returns now a list of booleans instead of the array of bytes. And so now you can see that reading from bit I plus 1 gives you the tail of what you would get if you read from bit I. And so this makes applying the induction hypothesis really natural. And then we have to prove that if you have the same list of bits, then you get the same array of bytes at the end. And in a nutshell, this shows that inductive structures are indeed better suited to do inductive proof compared to arrays of bytes like in the original code. OK, so now let's discuss the ACN codec primitives. So the ACN codecs is structured in a similar way as the bit stream. So it also offers primitive encoding and decoding functions. For example, we have functions to encode and decode 64-bit integers within some interval. And so the verification follows the exact same approach. And it relies heavily on the correctness of the bit stream. So I want to point out now that we did not prove the correctness of the floating point numbers functions because Stainless does not support floating point numbers. And we did not prove the invertibility for string-related functions because they are very rarely used. So I won't go into more details about this proof because it's the same scheme as what we already saw. But I want to show you this trick that we used at some point because I think it's interesting. So this is an auxiliary function that happens to be in this codec. It's not very important to understand what it does, but it takes an unsigned integers and converts it to a signed integers by considering only some bytes. The important part is that at some point we have this loop. So again, the details are not very important. The important observation is that the number of iterations is bound by 7 here. And so to do the proof, we had to come up with a while invariant for this loop to prove the properties we needed. And this was really tricky and time-consuming. And so at some point, we thought, why just not unroll this loop entirely, because we know that the number of iterations is quite small. And so we did. And now the proof was completely automatic because Stainless was able to reason about that and not about the while loop. And so this shows that sometimes it's easier to refactor your code rather than trying to prove it at all cost. OK, so to conclude about the static primitives, let me give you a few statistics. So the bit stream is around 3,700 lines of code, proof and implementation. And the ratio is about 5 lines of proof for 1 line of code. And for the SN codec, we have around 4,000 lines of code. I did not compute the ratio, but it's rather similar. OK, so now we can discuss the generated code part, and specifically how we tailored the code generation for the verification. So again, the high-level idea of the proof is exactly the same because the code looks similar, just that now everything is generated, so we need to generate the proof automatically. And so we needed to tailor the generated code for the verification. So now I will show you two ways in which we did that. So one first observation is that in the original backends, decoding was using in-place mutation for decoding, which means that decoding functions would receive an empty buffer, and they would decode the value and write into that buffer. But this was incompatible with the aliasing policy in Stainless. And so we had to move to a more functional approach in which decoding functions return the decoded value. But now the question was, how should we treat sequence of? So sequence of in ASN1 is an array of values. And so how should we treat them? Like, should we return an array that we allocate within the decoding function? Or should we append the decoded elements to some given collections? And so to answer this question, a really important observation is that sequence of could contain other sequence of as values. And so the problem we have at that point is that if you use arrays, you would have mutable arrays within other mutable arrays. And this, again, is incompatible with the aliasing policy that our tool supports. And so we had to find another way. And the solution we took was to replace the arrays by vectors. And so in the Scala world, a vector is an immutable collection that offers rather performant operations like the append, prepend, init, and tail is done in amortized constant time. And the random accesses, which I used in our project, are in O of log n. And this performance was acceptable for our use. And so then we used this instead of arrays, and we used lists to specify the content for the verification because list is better supported by our tool for now. And by the SMT solvers as well. OK, so now we can discuss the verification itself. So again, we go through our steps. So first, runtime safety. So the approach is exactly the same. We again have to prove how many bits is written or read by each function. The crucial observation here is that now the size is unclear because we are generating the code. We can't really know in advance, like while writing the compiler, how many bits we would read or write per function. So we have to generate a size function at the same time. And so if I can show you this example, so here we have another message in ASN1, which is a choice. So it could be either a sequence of 2 integers, so a record of 2 integers, or just an integer. And so now the size looks like this. And now you can see that when you decode a message of that type, you have to check whether you have the flag choice 1 in your bit stream. And if that's the case, the size is given by this formula. And otherwise, you have to check for choice 2, and it's given by this formula. And so the principle of proving the runtime safety is the same, but the proof was a bit more tricky because of that. And for the semantic correctness, again, the approach was similar. It was relying heavily on the bit stream and the codec proven properties. And the only main difference is that now the proof is generated. So we have to generate the specifications. We have to generate the lemmas to prove the specification. And we have to generate the lemma applications at the right place within the code so that, and this was the main, our main objective, that everything verifies automatically without any human interaction after the code is generated. And so I won't go into more detail about this proof, but I invite you to read the paper if you're interested. We have more details there. So now I want to show you a few experimental results that we have. So we tried our system on different packet formats for the real world. So we tested on the PUSC services, which is a set of around 300 packet formats, and it stands for Packet Utilization Standard C, and it is the standard specification used by ESA satellites and ground control. And it is used nowadays in 2 missions that are currently in space, CAOPS, which is an exoplanet transit observation mission, and PROBA3 to demonstrate a tandem flight for satellites. And the other set of formats we used was TC packet, which is the telecommand packet formats for ESA to send commands to satellites. So we generated the code and we ran the verification on both the static primitives and all these packet formats generated code. And we ended up with this, so around 335,000 VCs generated in total. And I won't go into more details about this, but you have the entire distribution. The 3 columns, so you have the library, which is these static primitives. And you have the formats for PUSC services and for TC packets. And so I gave you this number so that you have an idea of the scale of this study. And so you know it's the largest verification project that we did with our tool to date with respect to the total number of VCs at least. Okay, and so to conclude, I will give you a few. Yeah.
What was U and I column?
So V is verified, U is unknown, and I is invalid. And so I can give you more detail about that maybe at the end of the talk.
That's okay.
So I will give you a few lessons. So first, we found some bugs within the existing backends. So I will give you a few details. So the first one we found was that the not a number bit pattern was incorrectly handled in the C and ADA backends. Specifically, some assertions would have failed. And so we found this bug while translating from C to Scala. Then we found that the alignment requirements of sequence, so this record type, was handled also wrongly in the C and ADA backends. And we also found that while translating C to Scala. Then we found that the choice pattern was wrongly decoded, specifically when the choice was optional and the flag given in an ACN format. And so we found this bug while writing the proof. And the last one was some missing validation checks for 7-bit strings that are encoded on 8 bits. And this bug was found by Stainless while running the verification. And so it's important to note that all these bugs are reproducible with Stainless. It's just that we happened to find them earlier in the pipeline, but you could also have found them at the end. And they are now fixed in all backends, so C, ADA, and Scala. And finally, I want to give you this takeaway that we learned during this project. It's that every step counts in this process. So as we were verifying some existing code, we had to perform a lot of refactoring because you have to comply with your tool, you have to simplify the reasoning about some algorithms, or you want to remove some patterns that are harder to reason about. And so you're refactoring a lot. And in our project, we found some bugs already at that stage. And then once this was done, giving this code to Stainless allows it to generate a bunch of VCs automatically that would try to verify the termination, the absence of overflow, the inbound accesses, and it can also find counterexample at that stage. And this means that even there, you would get some guarantees, even if you haven't write any specification yet. And so the takeaway is that every step of the process is actually providing some valuable guarantees. And so to conclude, in this project, we added the new verified Scala backend to the ASN1 SCC compiler that is used by ESA missions. And to do so, we re-implemented and verified the static runtime library, specifically the subset used by the packets we were analyzing, to be crash-free and invertible. And then we modified the code generator to generate proof alongside the Scala code to be able to also verify the crash-free property and the invertibility, specifically for the sequence encoding. And we hope that with this project, we were bringing better reliability in space communications. And so I'm thanking you for your attention, and I'm happy to take any questions.
Hey, thanks. That's great work. So this is in Scala. You have got arrays of bits. They are heap allocated. I guess it runs on a JVM.
Yeah.
Is this like good and efficient enough for to be run on a satellite?
So it won't be run on the satellite. The Scala backend is used for the ground control station, on which you don't really care about that kind of performance. So we have in Stainless a backend that would generate some C codes that could be embedded, but we didn't use that in this project. And so our Scala code is intended to use only on the ground control stations. And so yeah, the arrays are heap allocated, and you have an array of bytes and so on. But it's on the JVM, and it's supposed to run on the ground control station's computers.
Okay, got it. Thank you.
So how much can you extend this to something like a JSON or a protobuf format that people use very often for serialization, deserialization? I mean, they have a lot of bugs too, right?
Yeah, so that's a really good question. I'm not sure how much of this particular work we could reuse because everything seems so tailored to exactly this particular compiler and this format and everything. But what I would say is that we learned during this project that if we want to do this kind of work, we should start from scratch writing a verified serializers and deserializer for this particular formats and not try to verify an existing one because I think the effort would be larger than starting from scratch. But this is an interesting point, and that's future work that we want to work on.
This is very cool stuff. Thank you very much.
Thank you.
This kind of serializing, deserializing has been it's seen a fair. It's a really cool application for sort of fancy verification, right?
Yeah.
And I think there have been a bunch of projects like I think what is the Adams group has something called Narcissus, which was in Cork. You probably know about that one.
Yeah.
And then the F-star people have done a lot of stuff with like packet protocol deserializing and so on.
Yeah.
So are there, have you looked at these other things? Are there some different kinds of constraints? I wonder, do the proofs sort of look similar in spirit or are they very different? Can you say a little bit about that?
Yeah, so I explored a little bit the Everest project from the F-star people, and I would say the idea is more or less the same. So they are also generating the proof alongside the code at the end. When I looked at it, at least, the generated code they were producing was not, because here what we are saying, like if you give a message format, you would get one function that could encode and decode this particular format. And then you have all the sub-functions that are used by this main one, but you still have this. In the Everest project, from what I could see, they were giving functions to read part of the packets because that's what the application was about with HTTPS and so on. You don't necessarily want to read the entire bit stream at once. And so they were giving more functions to access some particular values within this thing. So the approach is a bit different. So they don't have this big wrapper function that would give you access to the entire message. But I would say the approach is similar. For the proof, I can't really say they look really different because the tools are different. And so that's mainly it. But I'm pretty sure that the core concepts about the proofs are similar. Thank you.
Okay, so next talk is the last talk of the session, and it will be about the formal verification of probabilistic deep reinforcement learning policies with abstract training.
Cool. So I'm not sure I understand everything, but it seems to me that the point of having this neural network to make this decision is because your sensors are not very clear and you don't have really a clear idea on what is right. And I guess my question is, yeah. Okay. Hmm. Okay. Right. So is the idea, because I'm imagining a situation like the adaptive cruise control, where if you don't stop, then you're going to damage something. So you run things through simulation to get, or how does that process work? As far as I'm imagining, we're trying to verify that it will stop on time, right? I guess the learning phase is unclear to me. Hmm. Okay. Hmm. Okay, so then once you've got your abstract, how are you determining what's safe and what's not again, right? Is it again through simulation? Okay. Hmm. Okay. Mhm. Mhm. Okay. Mhm. So can we get a guarantee of like within some certain percentage probability that we won't ever hit this bad action? Is that what we're getting out of it? Okay. Cool. Thank you.
Thanks for the nice talk. So you only verified the safetiness of the MDP, right? So you couldn't get some theoretical guarantees about the behavior of the original deep neural network. Is my understanding correct? So there is some theoretical guarantees to say that. Uh-huh. Yeah, thank you. That's nice.
Thank you again for your nice talk. Just announcement, the lunch is at the third floor as yesterday for people who were here. There are several places where to take food and they are all the same, so please spread around and not making only one.
Welcome everyone to this afternoon session of VMCAI. We'll have 3 talks, and the first talk is by Isabella Mastroeni on abstract local completeness.
Okay, thank you. So, welcome to everybody. In this work, I will show how we exploit a strong connection existing between 2 notions for modeling properties of programming languages. That are this connection is really strong and provides different points of view, different perspectives on the same aspects. So local completeness is the standard way used in abstract interpretation for modeling precision of abstract domains, while abstract non-interference is a notion of a hyperproperty, is a notion that was introduced for language-based security, but then generalized, and that provides a deep insight in the way of properties of the inputs may affect properties of the output. So there is a strong connection between these 2 notions, and we exploit them to provide a new insight in the notion of completeness, a new way of looking at completeness. So let's start from the introduction of completeness. Very high-level introduction. I mean, in abstract interpretation, usually we have soundness. So we have the semantics of a program, in particular, and that may fail to be decidable, to be computable. But we want anyway to provide an answer to the whether these semantics satisfies or not the specification. So since the program, the concrete semantics is undecidable, we usually try to prove whether a property of the semantics satisfies the specifications. So we clearly, when we write something like this, we have anyway an abstraction of the concrete semantics. So still we have the decidability problems. And this means that we need to compute an abstract semantics which soundly approximate the abstract property. And in this case, if the abstract semantics satisfies the specifications, that by inclusion we have also that the concrete semantics satisfy the specification. Anyway, as already just observed, we may have false alarms because the abstract computation may introduce some noise, and this noise may lead to fail the inclusion relation of the abstract computation in the specification, and this means that we cannot say anything about the concrete semantics because we lose the inclusion relation. So what we can do is just to try to keep this abstract computation as closer as possible to the real abstraction of the concrete semantics. And indeed, when we have completeness, it means that the abstract computation precisely compute the abstract property of the concrete semantics. And in this way, if we are able to prove that the abstract computation satisfies the specification, then we can more easily, with more precision, provide the answer for the concrete semantics. And this is completeness. Anyway, clearly we have however, we add anyway some noise, which is the fact that we consider a property of the concrete semantics, and there are other approaches like adequacy for trying to control in this kind of loss of information. But when we have completeness, we clearly keep this loss of information as small as possible. So this is completeness, and it is usually described as a property of the abstract domain on the concrete semantics, and it is usually introduced as a universal quantified property. So we have completeness if for any possible input we have this equality that holds. And this is a problem because completeness as a static analysis is an intentional property, so it strongly depends on how the program is written. And since it is also universal quantified, it is a really strong property and very hard to be satisfied by a generic program. So recently it has been weakened with local abstract completeness, and which requires the completeness only on a specific input or set of inputs, with making really a local and focused property. So the relation
with absolute interference, so this way that we are going to, that I'm going to show, the look at completeness as an hyperproperty, allows us to find an intermediate weakening of completeness that makes it maybe more useful for characterizing precision. So let's see what is absolute interference. As I said, it is a notion introduced in language-based security, but then generalized in, as a generic property on programs. And it is an hyperproperty because it doesn't hold on single computations, but it holds on sets of computations. In particular, it is a two-hyperproperty because it compares pairs of computations. And usually it requires that for any possible x, so here we have 3, for example, we take the set of all the elements with the same abstraction, so the abstraction of x for all the possible inputs. We consider the computation of the semantics on these inputs, and we consider the property of the output of these semantics. So what is the requirement? This is the context. These are the ingredients that we consider for absolute interference. The requirement is that for any possible y, value y, input y, sharing the same property of x, for each x, the computation of the concrete semantics must have the same abstract property as the abstraction of x. So values with the same abstraction in input must have the same abstraction in the output. And this has to hold for all the possible inputs x's of the program. So we have a double universal quantifier, but it's double because we have to compare pairs of computation. So this corresponds precisely to completeness. It has been shown, formally proved, that requiring that for all x, requiring this kind of condition corresponds precisely to have completeness for all the possible inputs of the program. Since it is a universal quantified property, then if we have at least one x for which there exists at least one value y that has a different output property, then absolute interference and also completeness doesn't hold. So this is a notion introduced in the language-based security and now compared, proved to be equivalent to completeness. And now, since there exists this local completeness introduced in the literature, we wonder what it means for the absolute interference perspective to be local as completeness. So let's focus on a single x, clearly, first of all. This was the original requirement. And at this point, we observe that to require local completeness means surely to avoid the universal quantifier on x, as for local completeness, but also it means to weaken the output relation for the values y sharing the same property of x. So when we make local completeness, we are weakening the notion of completeness not only from the point of view of the quantifier, because we fix only one x, but also from the point of view of what we require as a property, as condition. So it is really a weak property. And also this observation suggests us that maybe there is an intermediate weakening of completeness, because we can still avoid the universal quantifier on x, but we can keep the same requirement as before in the output. So we decided just to investigate what is the meaning of just requiring the relation of absolute interference only on a fixed x, allowing anyway y to move to be universal quantified clearly only in the set of all the elements with the same abstraction, and requiring that the output must be the same, must share the same property as before. This is a new notion, and indeed it doesn't correspond neither to absolute interference because we change the quantification, but also it doesn't correspond to local completeness as it was introduced in the literature. And we call it a local abstract completeness because in this case we still are localizing the observation, but not on a concrete value, but on an abstract value because we fix alpha of x mainly. And this is still the same property as before, but only for one x. And if we compare it with local completeness, it means that we are requiring local completeness on a set of inputs, which are all the inputs which share the same abstraction as X. So the idea is that we have local standard completeness, which is a universal quantification on X, and we have local completeness, we just fix one X, and we have absolute local completeness, which fixes X, fixes the property of X, and requires that completeness holds for all the elements inside this set. And the interesting aspect is that by changing the abstraction, we change the property. Because if we take as abstraction the top abstraction, we get back the global completeness. While if we take as abstraction the identity, we get back the local completeness. But in the middle, we can just tune the way we are looking, the dimension of the sets we want to consider for checking completeness by using this abstraction. So let's see on an example, very easy, very simple example. We consider the standard sign domain, the most representative sign domain. So we have greater than 0, different from 0, equal, lesser than or equal, and greater than or equal. And we have the function making the square of the successor of X. And we wonder whether this domain is complete, globally complete, for the function f. So we take, for example, the input c, minus 2, 0, 2, and we check what happened for sign f, sign, which is the absolute computation. And we see that, indeed, we obtain as absolute computation the sets of all the greater or equal than 0 numbers. Because clearly the square of the successor takes, if we have minus 1, takes also 0, not only the greater than 0 numbers. So let's see what happened to the abstraction of a concrete computation of the same value. In this case, since we have minus 2, 0, and 2, we only get positive numbers. And then we get only positive numbers as a result. So we have a loss of precision. So we don't have global completeness because we have found an element on which completeness doesn't hold. So let's see another possible input. In this case, we take minus 1, 0, 1. We again consider the absolute computation of f. Clearly, this computation is precisely the same as before because the abstraction of this c is the same as minus 2, 0, 1, the same signs. But then we compute the abstraction of the concrete computation. And in this case, we have minus 1 that introduces 0. So the abstraction is precisely the same, all the elements greater or equal than 0. So in this case, local completeness holds. So we wonder whether absolute local completeness holds. And we observe that the two elements we considered, minus 1, 0, 1 and minus 2, 0, 2, have the same sign abstraction. So they are precisely a candidate for checking whether absolute local completeness holds or not. But unfortunately, we have, as we observed before, we have different results for this output observation, I mean the observation of the computation of f, and therefore absolute local completeness, in this case, for this abstraction, doesn't hold on these points. So in this case, we have local completeness, at least on one point, but we don't have absolute local completeness, and clearly also, we don't have global completeness. Let's see another example. We take this input element, 0, 2, and 4, and we first compute the abstract execution, and we get back all the positive numbers because we lose the 0 in the abstraction. And we compute the abstraction of a concrete computation, and again, we lose the 0, and so we get back to the same value. So in this case, we have local completeness on this point. So again, let's try to see if, in this case, we have or not absolute local completeness. And so let's consider all the elements with the same sign abstraction as C, which means that we take all the elements where there is 0 and at least one positive number. For example, 0, 3. And let's check what happened with the absolute computation. The absolute computation provides all positive numbers. And if we compute the abstraction of the concrete computation, then we have, again, the same absolute value. And since it depends only on the fact that we have 0 and all the positive and at least one positive number, which is precisely the fact that they have the same abstraction, clearly it's easy to check that in this case, for these points, we have absolute local completeness. Okay, so this was an example just to show that indeed we are in the middle. We are really in the middle between local completeness and global completeness. And that the fact is that we can tune the set of elements on which we have to check completeness by using this abstraction. So which was this is the definition of the completeness. The first thing that we characterized was to understand when an absolute domain satisfies absolute local completeness. In this case, there is a slight difference as before because we have two different abstractions in input and in output. In general, this is the most general characterization of both of completeness and absolute interference. And in this case, it's necessary because you are transforming, if necessary, the output abstraction. So we keep them maybe different. And in this case, what happened? We define this predicate blind, which is defined in terms of what we need. And if all the elements of the output observation are satisfy this predicate, then we surely have absolute local completeness. How it is defined is predicate. We consider a concrete element, and therefore the abstraction of it, A, is the abstract element we fix. Then we take all the elements with the same abstraction as absolute local completeness requires. We compute the concrete semantics, it is a definition, and we take this set depicted in green, which is capital gamma of A, which is the set of all the elements that must have the same abstraction to satisfy absolute local completeness. So we say that an element in the output observation D is blind if it is unable to break any of this set. What it means formally? It means that if it is greater than at least one of the elements in this set, then it is greater than the list upper bound, namely greater than all the elements in the same set. In this way, it is unable to break this set, and unable to break completeness. So if the output domain, all the elements of the output domain satisfy this property, then with respect to A, then we can say that the absolute local completeness is satisfied for A. And how can we use the same transformation for having the same abstraction in input and output? We just apply a fixed point iteration. And in the worst case, we get the top, clearly. But we reach a fixed point. So this is a way for simplifying domains towards absolute local completeness, because if we have an element which does not satisfy this condition, we just keep only the elements. We erase all the element D that cannot satisfy this predicate blind, and we keep only the elements that satisfy this predicate, and they form an absolute domain. So it's, I guess, still an abstraction. So this is a formal representation, just to better understand how it works mainly. And but if we want really to compute, to verify local completeness, then we need some more effective process for checking whether the property is satisfied. In this case, since our approach is language independent, we consider a very simple language, is a regular language, where the expression is the language of the basic statement, so for example, assignment and skip operation and guards. And then we have the sequential composition, we have the branch, and we have the loop iteration. So when we can define the absolute semantics depending on the absolute domain we are considering. And then we can prove a triple, where we have 3 elements, which is the first one is the input that we fix. So the input for which we want to check whether the abstract completeness holds or not. Then we have the other element is the program R, and the last element D is just the characterization, as we can see later, of the output observation that we have when we compute the abstract semantics. So when we are able to prove in our proof system a triple like this, then we are implying, is a stronger condition, but we are implying that abstract local completeness hold for all the elements C prime sharing the same abstract property as C. And in particular, we have two conditions that are satisfied. First of all, we have abstract local completeness, which is given by the equality between the first and the third element of this equation, because the first one is the abstract computation of the program on the abstract value of C. And the last one is the abstract value of the concrete semantics of C prime. Should be C prime. It's the same because half of C is equal to half of C prime, so it's not important. But anyway, this is completeness. And we also require that the abstraction of D is precisely this output value. So we have two conditions, and this way it is stronger, what we prove with our proof system. We have completeness, abstract completeness, local completeness, and we have the absolute value of the program, the concrete program on the concrete input. So this is the proof system. We have this very simple set of rules. The first rule transfer allows us to, we have to prove directly local completeness on expressions, which are maybe assignments and guards. And so when we can prove local completeness, we have the triple holding. Then we have the relax property, allowing us to relax the input or the output value in order to can apply the other rules, like sequential composition, where, as you can see, the output D prime must be the same as the input value for R2. So if they are not the same, we use relax for making them, if possible, making them the same value. And also we have the iteration and the recursive rule for loop iteration. And also in this case, the relax rule is important for the rec rule in order to make D prime and C or D prime corresponding. And then we have a rule for the join operation, so for the branch, and that allows to combine the output values when the inputs are the same. So with these rules, we can prove whether a program soundly satisfies absolute local completeness. So it is clear that this proof system is only sound, it's not complete. So if we can prove that a program with applying this rule satisfies the triple, then we have absolute local completeness. But if we are not able to prove it by using these rules, it doesn't mean that it does not satisfy absolute local completeness, because we are proving something stronger. So just a final example for the application of these rules. We have a very simple program, and we have as input minus 100, minus 10, and 0. Clearly, the absolute domain is sign. And we wonder whether this program satisfies absolute local completeness for this input, concrete input. So we can prove that the first guard x less or equal than 0 is local complete for the provided input. And we can also prove that the assignment x takes x multiplied by 2 satisfies local completeness, absolute local completeness for the input, which is the output of the guard. So we can apply the sequential rule, and we obtain that the sequential statement satisfies local completeness. And there is also the star that is missing here anyway. And then we can prove local completeness of the other guard. And in the middle, I forgot to put the rule for the loop iteration, but it holds. And finally, by applying the rules, we can prove that the whole statement satisfies absolute local completeness with respect to this input statement. And we have also that the abstraction of the the absolute property of the output is equal 0 in this case, because we have the precise value in the absolute domain. So this is the idea of the application of the rules, just for proving that we can indeed prove some interesting absolute completeness properties. So concluding, we introduced this approach, formal approach for characterizing, for weakening, and also tuning completeness, because as I said before, completeness is a strong, really strong property because it is intentional, it depends on the way the program is written, and it is universally quantified. And this is a problem, so it may be a problem, so we need to weaken this property. Local completeness is an interesting weakening, but it goes directly on the opposite side. It's focused only on single inputs. So this was an intermediate way just to, as I said before, tuning on which set of elements we can prove completeness. Anyway, the fact that it is intentional may be also exploited for other interesting results. So we can try to design program transformations for making program complete or incomplete for a specific absolute value. Some transformation like this exists for global completeness, exists for absolute interference. So maybe we are able to characterize them also for absolute local completeness. Why this could be interesting, for example, for incompleteness, because it has been shown that completeness is a way for characterizing, for example, obfuscation, because if a program, we want to obfuscate a program, we just make it incomplete with respect to what we want to hide. But since the completeness is very strong, weakening completeness is really weak. So this is, again, a way of being in the intermediate part. And also we can try to combine with metrics, so obtain some kind of partial. Instead of requiring the equality, we could require just to have a distance between the results and to understand. It has been defined for completeness. We would like to see what happens for absolute local completeness. That's all.
Okay. Thank you. Okay, questions? I'll kick off the discussion and then let people pick up. So it's really interesting the use you make of regular expressions to do these proofs. And you showed these syntactic rules. Can you put the slide? I actually had two questions, one technical and one just more general. The rules for recursion don't guarantee this is the least fixed point. Is this a problem or is it's fine? You
it's
just
fine.
Want to unfold, basically.
Yeah, exactly.
And the other question I had, I mean, it is known that for regular expressions, a more semantic-driven reasoning can be more efficient in computing not only that the proof is correct, but also that you can find counterexamples more easily. Have you tried anything in that along those lines, using sort of by simulation-like reasoning, or have you only done the syntactic?
No, we only made the syntactic. We are investigating different way of looking at this. Semantic ways surely can be a very interesting direction, but also incorrectness. I mean, if it is useful for understanding when it doesn't hold. If we can characterize for which absolute points we are complete and for which we are not.
Yeah, that was exactly.
It's working in progress. Yeah. I mean, we are thinking of it, we are working on it.
And the last question, I mean, early in your talk, you were talking about hyperproperties and how these things are hyperproperties. Did you exploit any connection with actually proof techniques for hyperproperties, or this was sort of just an observation at the beginning?
It's a dream of work. I mean, we realized when we modeled absolute interference, we realized that absolute interference was an hyperproperty. We investigated from the semantic point of view. And we had several discussions also with Patrick about logics, and he has a POPL paper about this, and also with Peter. And is a way, a road that we want to make, and something we want to study, but still we don't follow that direction yet.
Okay, okay, cool. Other questions? Okay, if there are no other questions, let's thank Isabella again and move on to the next. Okay, so the second talk of this session will be given by Jared, and he's going to talk about an abstract domain for heap commutativity.
Let's see if I can get my mouse to work as a makeshift slide clicker. Pretty good. Okay. All right. Hey everyone, I'm Jared, and like Alexandra said, I'm going to be sharing an approach for commutativity analysis in the context of the heap memory model. So for those unfamiliar, commutativity is a relational property of programs or fragments of programs, which we denote with this bow tie operator. And it holds when executing the two programs in sequence yields the same outcome regardless of the order of execution. This property is growing in popularity in a variety of domains because if you can swap the order of execution, that grants a sort of independence which is more broadly applicable than a strict requirement of disjointness of the operations of the two programs. The goal of commutativity analysis is to find a so-called commutativity condition on the initial state under which your two programs commute. And naturally, when you're synthesizing a condition like this, you want it to be meaningfully weak so that it occurs as often as possible. And aside from synthesizing a condition, you might also try to propose and verify one, which naturally is easier to actually execute on. But one context where commutativity analysis is underexplored is in the memory model of the heap, which is why we're going to target it in this work. So to start with a basic example, let's consider a typical implementation of a stack data structure on the heap. And it comes with operations for push, pop, and peek. One question we might ask is, when does pushing a value u commute with pop? Well, actually, before we can answer that, we have to decide what we consider equivalent outcomes to be. Now, there's a pretty straightforward one. In this context, let's say that we consider equivalence to be when the resultant stacks on both sides are observationally equivalent. That is, they contain the same values but may have different intermediate addresses, and that our return values of our push and pop operations are the same. So in particular, pop should return the same value in both cases. With this, we can find that the weakest commutativity condition for this program pair is that our initial stack has at least one element, and that element is the same as the one that we are pushing. So how might we show that this is a valid condition? So you might go to employ typical relational reasoning techniques, but they tend to be kind of ineffective in the context of commutativity because, in general, we're trying to compare F sequenced with G and G with F, and those usually have dissimilar shapes. So they lack meaningful alignment points, and the ways that you would typically decompose a relational problem like this don't become so useful, which means that proving this tends to amount to 4 symbolic executions for every program pair. So as your number of programs grows, the total number of executions you're having to do grows quadratically. It's not great. Now, particular to the heap, there are a couple extra frustrations to contend with. You have to consider whether your heap is well formed in the first place. So in the stack example, for instance, for these programs to commute, you need the stack to actually be well formed on the heap to begin with. And similarly, we have to contend with observationally equivalent heap structures, like having different intermediate addresses in stacks with the same values. And relatedly, this ends up coming from the non-determinism of address allocation. So what we sought to do was wrap all these things together and leverage abstraction to be able to work with this problem much more straightforwardly and simply. So with that in mind, and the abstraction we've designed, here's what our technique looks like in broad strokes. So we want to analyze the commutativity of our concrete program pair. The first thing that we do is we lift our concrete programs and our heap structures into our abstract domain, then establish a soundness relationship between our concrete and abstract programs, then analyze commutativity in the abstract space, which we'll see is way, way easier because we're going to be working with pure mathematical functions over mathematical objects, for which a variety of tools and techniques already exist to do that kind of analysis very efficiently. And then finally, we will have a sound commutativity theorem which lets us immediately derive concrete commutativity conditions from our abstract analysis. And in particular, the resultant conditions will be framed. That is to say, if it guarantees that if F and G commute in any particular heap context, they're also going to commute in any larger context, and we get that for free. And along the way, as I mentioned, we will easily capture observational equivalence, heap well-formedness, and as we'll see later, will also support composition of disjoint heap structures. So let's talk about what our domains look like. First, the concrete domain is simple. It's sets of heaps. Not individual heaps, but sets of heaps because, as we said, our concrete programs can be non-deterministic, so we want to account for the possibilistic outcomes of our heap program executions. Now here's where the new stuff comes in. The first ingredient for designing our abstract domain is that we pick some set of abstract values x. These could be lists, integers, Boolean sets. The choice depends on what heap structures and behaviors we're looking to lift into the abstract space. So we'll see shortly that for our stack, for instance, we may choose lists of values as a meaningful abstraction. So then in our domain, we create a lower bound of bottom, which will represent failure, and an upper bound of this little smiley face, which represents sort of an ambiguous combination of abstract elements, and we'll see the complement to the smiley face in a moment. The natural question is, how do we connect these two domains together so that we have a sound relationship? Well, our second ingredient to help this out is going to be designing a projection function pi, which maps heaps into our space of abstract values. But if you recall, we said, for the case of the stack, for example, our abstract values are lists. What if we have a heap which does not have an appropriately allocated stack? What do we do with it? Where do we map it into the abstract domain? Well, this is where we have a special abstract value come in, call it frowny face if you'd like. And this abstracts the heaps which are not well formed with respect to whatever lifting we're trying to go for. So we can add that to our domain and then top off the domain, as it were, with top. From here, now we can build our abstraction and concretization functions, which form a Galois connection. In particular, the abstraction function is real simple, takes a set of heaps, projects all of them using pi, and then yields the least upper bound of all of those results. What we get from this is sort of two key pieces to...
Can I ask a question?
Yes?
When you take the least upper bound there, because you took a flat domain, is it the case it's always going to be smiley face or close?
No, so if you have a set of heaps, so the question is, if you're taking the least upper bound, wouldn't it always just go to smiley face or top or something? No, because if you have a set of heaps, which are all, they may all map to the same abstract values. So for instance, if you have multiple concrete stacks with different intermediate pointers, but the same values within them, they'll all map to the same list of values. And so they will all end up here, for instance. As soon as you have two different ones, yes, it'll go to smiley face, or if you have something out here, it'll go to top, yeah. And we can address that more later. So what we get from this connection is sort of two key pieces to our abstract domain. The first characterizes heaps which are well formed with respect to the lifting that we've created, and we call this the purview of our abstraction. It is the heaps that it can understand and reason about meaningfully. And then in contrast, we have this piece of the domain which we consider to be the heaps that are out of purview. They have structures that our abstraction cannot understand, and therefore when we perform abstract commutativity analysis, if we get results that involve frowny face or top, we've lost precision and we won't be able to draw meaningful conclusions back down in the concrete space. And then just one more detail, we add an extra requirement to our projection function called a locality constraint, which says that if we have some heap which is in the purview of our abstraction, then any larger heap should map to the same abstract value as the original. So let's look at an example again of how this all shakes out with our stack. So like I said, we might choose for our abstract values to be lists to represent the values inside of the stack. And then the way we might build our projection function is using some separation logic style heap predicates. We would say, all right, given a heap, map it to a list S if those values in that list correspond to the values in the stack. Otherwise, if there isn't such a list, map it to frowny face. Now the stack predicate there is doing a lot of the heavy lifting. How we might implement that is with a very standard recursive definition of a well-formed stack on the heap. And just as a refresher on sort of these separation logic style predicates, we have the points to predicate, which says that the address head points to the value p in this case. And then we have the separating conjunction, which says that the heap has to satisfy both sides of the conjunction, and also both sides need to use disjoint sets of addresses. Then one more detail, we annotate this predicate stack with the plus to indicate that the heap may contain a valid stack rather than having to be exactly a stack. So we have our domains. Let's look at our programs in the concrete and abstract spaces as we sort of build up all the pieces of this diagram. So as we've said, concrete programs map heaps to sets of possible heaps. We aren't super concerned in this work with the specific concrete semantics, but so here's a sort of general implementation that you might see of push, pop, and peek for the concrete stack. You have your typical operators of address allocation, dereferencing, freeing, writing. The key thing to note here is that each of these operations has an input or an output value, but instead of having sort of this floating either external input or return, we actually provide an address to have the input get read from the heap or the output get written to the heap, so that now everything is taking place on the heap. And that makes the connection, reasoning about these concrete programs in the abstract space a little more straightforward. Now, abstract programs, as we said, they are pure mathematical functions operating over the values in our abstract domain. So looking at an example, now we have a nice simple implementation of push in our abstract space, extra cell with its input argument. So in fact, this is going to be the case for all three of our operations. The abstract values for us to work with when defining these operations stack, but also an extra cell of sorts to encode either this input or output. So indeed, you can see with push, what it yields is that final push stack, and then it preserves that extra cell, which at this point is arbitrary because it's not outputting anything in particular. Similarly, we can define pop and peek, where they disregard that initial input, but then they use that extra cell in their output. We can see that here. And then just as one other note, when we try to pop an empty stack, you can see that we yield bottom, which indicates failure. So we have our concrete and abstract programs. Let's connect them together with a notion of soundness, which we denote with this squiggly arrow. And we say that abstract program M is sound with respect to concrete F if two things hold. First, that M over approximates F, which is a standard constraint in abstract interpretation. And then a second one, which says that M fails when F fails. And the second one is important because our notion of commutativity is going to depend on successful termination of the concrete programs. So this helps to handle that case. And the way that we would show this is using typical symbolic execution techniques. And note how now what we've done is we've said, OK, for each program, if you have n programs, for each one, show soundness once with its corresponding abstract program. And then we'll reason in the abstract space instead of having to do those 4 symbolic So now let's actually define commutativity, both in our concrete and abstract spaces. And then we're almost there. Then we can get to our sound commutativity result. So in the concrete space, we say that our two programs commute under a commutativity condition, a heap predicate P, and with respect to some relation on the output sets of heaps, if given a heap that satisfies that commutativity condition, executing F sequence with G on that heap gives an equivalent outcome to G sequence with F on that heap, and that both sides successfully terminate so that we actually get a non-vacuum, a meaningful outcome and no failure. You could instead define concrete commutativity using a co-termination sense, but here we're going to stick with mutual termination, or both termination. Correspondingly, in the abstract space, we say that our two programs commute under a predicate Q on our set of abstract values if given an abstract value that satisfies Q, executing n composed with m on that value equals m composed with n, so the flipped compositions, and critically, that the result is in our meaningful section of the abstract domain X. And this is because you can imagine if both results went to top, you'd say, OK, great, they were the same outcome, but we don't know anything about, top doesn't tell us anything meaningful. So we restrict what the meaningful section of commutativity is in the abstract space, which then lets us get to our sound commutativity result, our last ingredient in this diagram, which says that if we have soundness between our two pairs of programs, supposing that the abstract programs commute under a predicate Q on our values X, then we can immediately derive that our concrete programs commute under a predicate P, where a heap satisfies P if it is in the purview of our abstraction, and the abstract value it maps to satisfies Q. Two details to note here. The first is that we said that concrete commutativity was with respect to some equivalence. In particular, here the equivalence that we get is that which is imposed by the abstraction. So in particular, we get that the results on either side of the concrete execution, if they both map to the same abstract value, then they are considered equivalent, which means that the projection function that we choose sort of induces the observational equivalence that we're interested in the concrete space. The second detail is that, again, we have that our concrete condition is framed with that plus, and like I said before, that means a guarantee that if F and G commute in any particular heap context, they also commute in any larger context. So let's put this all together with our stack example. Here we have all the possible program pairs for our 3 stack operations. And like I said, we aren't too concerned with the technique in this work, but you can use some either manual or automatic mathematical analysis over these functions and objects to find, in this case, the weakest possible preconditions for each of these program pairs. And these conditions are in terms of the initial stack, the list of values S, as well as the potential input arguments to push U and V. So question is, how do we then construct our concrete condition? Well, that sound commutativity theorem gives us a sort of procedure for doing so. What we do is we say that our concrete condition will hold for a heap if that heap contains a well-formed stack and contains the input or output cells for the 2 programs, and those values corresponding, the list of values for the stack and the values in those cells, those satisfy whichever particular abstract condition we're using for each pair. So then what we get is we can immediately construct derived concrete commutativity conditions for each pair. So note, for example, that for peak and peak, we get that they always commute in the abstract space. But what that translates to in the concrete space is that we at a minimum need that the initial heap has some valid stack and some valid input-output cells. And then the rest doesn't matter because the abstract condition was true. As one final topic, I mentioned earlier that this is amenable to composition of disjoint heap structures. So let's suppose that we have 2 abstract domains, A and B, which each have their own projection function and set of abstract values. We can build a domain A star B, which is analogous to the concrete separating conjunction. So if these are our 2 abstract domains, what happens when we compose them is we don't take an actual product over the entire domains. Instead, the main structure stays the same, but our specific abstract values become all possible pairs of the A values and the B values. And then, when we are mapping a heap into this compound domain, it's in the purview, so to speak, if we can partition that heap into 2 halves, which one half maps into A and the other half maps into B, in which case the value that we map to is the pairing of that A value and that B value. And of course, naturally, those 2 halves have to be disjoint. So one way, there are various nice properties that we get from this composition. Here's just one example that we elaborate on in our paper. Here again, we have the results from our analysis of a stack data structure. Let's say that we have another data structure, a non-negative counter that has increment, decrement, and read operations. And again, we've synthesized or verified using these mathematical analysis techniques commutativity conditions for each of these pairs based on the initial value of the counter. Now let's say that we want to design a concrete data structure that has both a stack and a counter so that we can keep track of the size of the stack. So the programs for that, at least in the abstract space, might look like this, where we say, oh, pushing now both pushes a value and increments the counter. Similarly, pop, there's a typo there, but pop pops a value and decrements the counter. And then peak does the same thing as before, and getting the size of the stack is just reading the counter's value. What's nice is that we can get for free the commutativity conditions for these compound programs, all possible pairs, just by combining the results from our two individual analyses. Now, naturally, we would then want to derive the concrete commutativity conditions for this compound data structure. Caveat, it's a little bit less free because we need a little bit of an additional guarantee about what happens when we compose our programs together. So in particular, for example, we would have to show that our sort of compound operation of push and increment on the independent structures is sound with respect to the concrete operation of, for instance, push sequenced with increment. And this tends to not be very difficult to do, but it is just one extra detail. Okay, so to summarize, we've designed a fairly simple abstract domain that lets you lift concrete heap structures and programs and lets you reduce concrete commutativity analysis, which can be rather troublesome, to much simpler, more automatable reasoning about pure mathematical functions and objects, for which a variety of tools and techniques exist for doing this efficiently. And along the way, we're able to collapse together observationally equivalent cases and similarly handle non-determinism of address allocation and also capture the well-formedness of the heap. And as we just saw, it is amenable to compositional results about disjoint heap structures. We have a bunch of things that we'd like to try moving forward with this work. The first is naturally to implement an abstract interpreter. So we've proven all of these results in Coq, but not in a way that's super friendly to automation. So we'd like to implement that and relatedly integrate our analysis with existing techniques for synthesizing or verifying abstract commutativity conditions, which, as I've said, there are various, there's a bunch of research into doing just that. And finally, and this sort of gets back into what Alexandra was asking before, we'd like to try enriching our abstract domain to have a lattice of sets of abstract values. This would allow our abstract programs to also be non-deterministic, and it would allow our concrete programs, if they're non-deterministic in a way that yields non-observationally equivalent outcomes, we don't completely lose our precision. We know, oh, here are the sets of values that are corresponding in the abstract space. And this would allow for us to analyze commutativity, for example, by seeing if the possibilistic outcomes of the two sequencings all match up or if there's a disparity. And we are interested in seeing if such an enriched lattice would then become even more broadly applicable to other heap analyses than commutativity. So that's what I have for you today. Thank you very much. And I'll happily take any questions.
Okay, questions? Yes.
It was a great talk.
Thank you.
I was wondering, so you picked a particular abstract domain to do all your analysis in, right, if I understood right?
Mm-hmm.
So I was wondering if you could sort of lift this to an even more broader theorem that said, you know, any abstract domain that follows certain conditions would suffice for this kind of analysis.
I'm sure that you could. The way that I talked about the development of each piece of that domain is basically how it went in our actual research about it, to be like, well, now you're going to need that frowny face, and you know. But I'm sure that there are ways that you could broaden it and say, well, as long as your domain has properties X, Y, and Z, then it would be amenable to this kind of analysis. Sure. Mm-hmm. Yep. Absolutely.
Okay. Other questions? I have a quick question. Are questions of decidability important on how you build your domain? I mean, as you were talking through your stack example, I was thinking that in one of your definitions, it felt like you would have to prove that two of those sequences were equivalent or not, so sequences of pushes and pops. And if you're not careful, when you add these commutativity conditions, you might end up with, you know, an undecidable problem, whether these two sequences are the same. And maybe this is not an issue in the way you set up your abstract domain,
right.
But I was actually wondering if there's any question of decidability of the two sort of programs. Or I know you alluded at the techniques, you get the abstractions coming from analysis, but I was not sure what were the concrete things in there.
I'm not sure. What I will say is you might have been able to tell from the examples I used, we haven't concerned ourselves much yet with loops. And I think the moment that you introduce like a question of actually not being sure whether something terminates and dealing with fixed points and these things, which admittedly I'm not super familiar with, I would imagine you start to run into certain problems of even showing the equivalence in the first place is like not super obvious, which maybe in that setting, something like sort of this approximation to say how close, like we can't be sure that they're exactly the same, but how close can we be sure that they get? And then, for example, so the way that this ends up getting used in the real world, so with my former advisor, Eric, we've been working on a project that's ongoing now of a programming language called Veracity, which is a C-style language where you can actually have these blocks of code that you want to commute, and it will find for you a commutativity condition and try to get it to be as weak as possible. And the idea is that, you know, it's not most things aren't always going to commute, but actually if they do, it turns out that with certain extra guarantees about serializability, you can get them to run it concurrently. And that's like the main approach of that language. And so what you could have, for example, is let's say that you can get to like 99% sure that the two outcomes are the same, and a checker to make sure, so you say, okay, run them at the same time, because we're 99% sure that this should be fine. And then check if there's an error after you've run them and say, okay, this didn't work, do it in sequence instead. But 99% of the time, you get that benefit of the concurrency. I don't know, but that's something interesting to explore.
Yeah, thanks. Okay, if there are no more questions, let's thank the speaker again. And we have one last talk. Let's set it up.
Probably want this, I realize.
Be useful.
Okay.
Can I suggest,
Yes.
because as you move this,
Okay.
if I can adjust this for you, I notice the presentation.
Perfect.
Okay, let's try that. Okay. Okay, so the last talk of this session will be given by Geoffrey on two-way collaboration between Flow and Proof in Spark. Go ahead.
Thank you. Thank you for having me. So hello everyone, I'm Geoffrey Huguet, and today I will present joint work with my colleagues Claire Dross and Johannes Koenig. The title of the paper is Two-Way Collaboration Between Flow and Proof in Spark. So there are various kinds of static and dynamic verification frameworks and tools, all with their weaknesses and strengths. And it's common to try to combine them, either manually or automatically, and trying to integrate different analyses in the same tool. Spark is a tool to verify programs written in the Ada language. It combines two analyses working as different paths. So there is data and information flow analysis and deductive verification. And in this talk, I will present these analyses and their collaboration. As Spark is focused on verifying Ada programs, I will do a quick presentation of Ada first. So Ada is a general purpose imperative language. Its first version dates from 1983, and throughout the years, new versions of the language have been released. The latest dates from 2022. It allows for low-level programming, but also offers higher-level features such as object-oriented programming and concurrency. As Ada is designed for safety-critical applications, it inserts language-mandated runtime checks. These ensure that nothing can go wrong, and we'll talk about that just later. And at runtime, in case of failure, they lead to exceptions. So for example, here, we have an integer y, and we are trying to assign it x divided by c. We have a runtime check checking that c is not equal to 0. When accessing an array component, like for z, we have a check to verify that the index is in the correct range. Ada has strong typing and also enables the user to define new types and subtypes with precise constraints. These constraints are also checked at runtime. So for example, here we have a small int derived from an integer which ranges from -100 to 100. When a user attempts to assign it, ADA inserts a check to verify that it's in the correct range. In ADA 2012, has been added contract-based programming to ADA. It allows to annotate subprograms. So subprograms in ADA include functions and procedures. Procedures are just functions that do not return a value. We can see that parameters have modes. So by default, the mode is in, which means that the value can be read. Here, x is an in-out integer, which means that it can be read and assigned. So we can annotate pre- and post-conditions on subprograms. So the precondition here states that x should be strictly less than the last integer, and the post-condition states that x is strictly greater than the value at the beginning of the call. Another example of contracts are strong and weak invariants on types. So here we have a sorted array, which derives from an array, and the predicate states that it's always sorted. With a compilation switch, it's possible to evaluate this contract at runtime. So an exception is raised in case of an evaluation to false. Spark attempts to verify ADA programs. So it does so statically without running the program, does so for all inputs of the subprograms. It provides a sound non-complete analysis, so it might have false positives. So first, it tries to prove language-mandated runtime checks, such as the range check or the index check that we've seen earlier, as well as the user-supplied contracts. So when calling a procedure here, increment, it will try to prove the precondition. When assigning a value to a type with a predicate, it will try to prove the predicate on the value. So in this presentation, we're going to look at the two analyses performed by the Spark tool. The data information flow analysis that we call flow, and deductive verification that we will call proof. I will present them and share how the verification objectives are shared between the two so that each works as its strength. The initial architecture is in black. Then I will explain the mechanism that have been put in place to improve the overall effectiveness of the tool by increasing the collaboration between the analyses. So on the one hand, flow, which runs first, computes information necessary for proof. So that's in red and the dashed line on the picture. On the other hand, some value-dependent checks are automatically deferred to proof to improve precision, as can be seen in yellow, the dashed dotted line. Finally, I will present a feature for which the handover from flow to proof can be requested on a case-by-case basis by the user. It's called relaxed initialization. So we'll start with the analysis that runs first in the tool, flow analysis. So flow analysis tracks flow of information between objects to detect dependencies. So it's based on the control flow graph of the program. It has the particularity of being fast and interprocedural, so it can see the whole program. But sometimes it's imprecise because it's not value dependent. So for example, here we have an example where all possible values of x are covered by the if conditions, but flow is not able to determine that sign is always initialized because there is a third hidden path, which is the else branch. Flow verifies contracts related to the program data flow. So here we have the set of global variables accessed by the subprogram, the dependencies between the inputs and outputs of the subprogram, as well as the potential termination of the subprogram. So in the example here, we have the procedure add v to g, which will update the value of a global variable g depending on its initial value and the value of v. Flow is able to prove that all the contracts are correct. For formal verification to be tractable, we need simplifying assumptions. They have two purposes. The first is to reduce the annotation burden on the user. And second, they improve the automated provability. One of these assumptions is a strict initialization policy that's checked by flow. So this strict initialization policy states that all inputs of the subprogram are entirely initialized before the call. So in the example here, in the procedure P, it's allowed to read X because it's an input of the subprogram. So as such, it's allowed to read it. However, it also states that all outputs are entirely initialized after the call. So given that flow analysis is not value dependent, it's not able to determine that sign is always initialized after the call. this has a benefit of not needing user-supplied initialization contracts, which can be very cumbersome to write. So now we've seen that flow analysis is a non-value dependent interprocedural analysis. It verifies contracts related to the program data flow, as well as assumptions like initialization. Let's move on to the second analysis in Spark, proof. So proof is called deductive verification. It takes ADA code annotated with contracts. From it, it produces logical formulas called verification conditions. These are sent to automatic solvers, so in our case, SMT solvers, and that verify them. And if all conditions are verified, the program and its contracts are correct. Because contracts are part of the ADA language, it means in particular that they follow the semantics of ADA. Regular ADA functions can be called inside contracts. They can have preconditions, so they might not be defined on all values. They can access global data and even modify it. And also they can potentially not terminate. These functions are mapped to logical mathematical functions in the underlying logic. These have the property of being total and described either directly, so for example, x gives x plus 1, or using axioms. In Spark, we have made the choice of not identifying logic functions, so all functions can be used. We have some conditions for that. They should not have side effects, and they should terminate on all inputs. They are translated to axioms, so that is, for all inputs satisfying the precondition, the result of the logic function satisfies the postcondition. But when we add axioms, when we introduce axioms in Spark, we do it with care, because if you are introducing an axiom who can be equivalent to false, you might be to prove anything afterwards. Such axioms are necessarily sound, provided the function terminates first, and second, the return value satisfies the postcondition. So here we have an example of a bad function whose postcondition is false. If we had to introduce the axiom for this one, it would translate as for all natural false. So this is an unsound axiom. Fortunately, while proving bad, Spark will check that there is no possibility for a return value to satisfy the postcondition. So we keep a sound analysis. Now we've seen flow that's fast but imprecise, and proof that's modular but more precise but slower. Proof checks everything that's not checked by flow, so absence of runtime errors and pre and post contracts. Now let's see how they collaborate. So first, flow computes information that's used afterwards by proof. So we've seen global contracts. The problem with the global contracts is that they grow with the call graph. So in particular, this means that they can be very difficult to maintain while you're extending your program. And second, they might not be interesting for the user. For example, the user just wants to verify absence of runtime errors. But these contracts are needed by proof. First, for precision, because the proof needs to know which data is modified by a call. Also, it needs this to be precise, because functions can read global variables, and they need to be treated as inputs of the subprogram. In the example, flow analysis computes an over-approximation of the global contracts, so that it produces the contracts for add v2g and read g. So, and in this way, proof later is able to show that the value of v was not modified by the call to add v2g, and the read value of g after the call is not the same as the one before. Another contract that can be generated by flow analysis are termination contracts. In general, Spark is only interested in partial correctness. That is, postcondition need only be valid if the subprogram terminates. But we've seen that non-termination can lead to unrealizable contracts, so unsound, that could introduce unsound axioms. So functions used in logic must terminate. Once again, flow analysis computes an over-approximation and checks termination of functions. So if we add a body to bad, and we call a never-ending subprogram, proof is able to prove the postcondition because it's never reached, but flow analysis will complain that the subprogram might not terminate. Something linked to termination is recursivity. Recursion in AIDA is not explicit, and moreover, it can even occur across different compilation units. But when verifying recursive subprograms, in particular logic functions, proof needs to make sure that the axiom introduced for the contract is not used to prove itself. Flow analysis, in this case, is able to compute a call graph. And if we take the bad example, we imagine that it terminates, and we add a recursive call in the post condition. If we added the axiom of bad, it would allow to prove the post, because it would state that for all natural, false. But when detecting recursivity, proof removes the axioms so that the axiom is not used to prove the post condition of the same axiom. So let's go back to the graph. Previously, we've seen that flow and proof run as separate analyses. And in this part, we've seen that flow is also used to compute information for proof. It generates various kinds of contracts, but also recursivity through a call graph. Now let's see how flow relies on proof to give a more precise analysis. So we've seen numerous times that flow analysis is not value dependent. In particular, it's not able to detect that a branch is dead because of some value reasoning. However, the user can inform flow analysis that a branch is dead using a pragma assert false. This assertion, like the post condition of bad previously, is only proved when it's never reached. So proof can show that it's never actually a dead branch. When encountering such a branch, such an assertion, flow cuts the branch, so it does not flow to the subprogram exit. Other flow checks, like initialization checks, are still needed on the branch because proof might rely on them. If we take the example with the sign, the user can now inform that the else branch is actually dead. And flow will prove that sign is initialized on all paths of the subprogram, and proof, which runs later, will prove that the branch is dead. Related to the dead branches, exception handling and propagating is supported in Spark. So here we have two examples. One procedure might raise E, which might raise E condition, E exception under the cond condition. This is expressed through exceptional cases contract. And then we have might raise exceptions, which might raise any exception and under any condition. Unexpected exceptions are exceptions that are raised, but neither caught, neither specified in the exceptional cases. When a subprogram raises an unexpected exception, this is considered as error signaling. And like the dead branches previously, proof checks that they never happen, and flow can safely cut the branch so that it does not flow to the subprogram exit. Another imprecision of flow is on loop termination. So for for loop, which operates on a range, the proof is automatic, they terminate. However, for other loops, there is a need for a variant. So in general, a variant is a mathematical integer which strictly decreases. In Spark, it's a machine integer that either decreases or increases, and since it is bounded, there will be a stopping case. When encountering such a variant, flow assumes that the loop terminates, and proof checks the variant later. So here, we have the example. If the while loop didn't have a variant, flow would complain that it needs a variant, and when encountering the variant, it just cuts this message and let proof check the variant. Also note that there exist subprogram variants which are used to prove termination of recursive subprograms. So after presenting flow and proof and how flow computes information for proof, we now know that proof is used for more complex check that flow would be unable to prove, like dead branches or a verification of variants. It does so by leaving the check, and checks are proved later when proof runs. So this arrow is actually the other way around because it's proof helping flow analysis. However, I decided to keep it this direction because I want to emphasize the fact that this does not require the program to run twice or anything like this. Flow always runs first and then proof, and there is no additional running of the program for flow to get information from proof. What we have seen thus far is always done automatically, so be it the computation of flow for proof or the handover to proof. So now let's focus on a feature where the user can choose between flow and proof to prove the checks. It's called relaxed initialization. So we've seen throughout the presentation that flow is not value dependent. In the case of proving initialization of variables, this could represent a problem. For example, on arrays initialization, if we do initialize them using slices of the array, flow, being non-value dependent, is not able to prove that the array is entirely initialized. Also, the policy on initialization might be too constraining. So for example, if you have a record is just a structure with 2 fields, for example, in this case, and you try to initialize it through different subprogram calls, because of the initialization policy, X is required to be entirely initialized at the subprogram entry, which defeats the purpose of calling initialization procedures. Improvements on this area are long-standing requests by our customers. So we could think about using proof to check initialization. Indeed, proof is value dependent, and we can specify initialization status of variables using the tick initialized attribute. So if you want to state that proof is now responsible for checking initialization, as a precondition of initf1, we should say that y is initialized. And in both condition, the initialization status of x.f2 has been kept the same as the subprogram entry, but the x.f1 is now initialized. And even though it sounds good, there are lots of drawbacks. So first, no initialization policy means that the contract needs to completely describe the initialization status of variable at the subprogram boundary. Like the global contracts, it can be very cumbersome to write. And second, there is a loss in proof efficiency because the proof graph is larger. Now, proof needs to take into account the initialization of all variables when proving any contract. So we chose to let the user decide between the two. So we have now an aspect called relaxed initialization that the user can annotate on objects, as well as on subprogram parameters and function results. So if we go back to the initf1, we now specify that x is relaxed initialized, and we keep the postcondition because it was correct as is. But what we gained here is that y still is subjected to the initialization policies checked by flow. When proving initialization of variables, proof considers the initialization of scalar subcomponents independently by attaching a flag, a Boolean flag, to state whether it's initialized or not. The initialized attributes evaluates all the flags recursively. So now you can call initf1, then initf2, and you'll be able to prove that y is entirely initialized after those two calls. Note that this requires no additional communication. First, there is a common routine to decide which analysis checks the initialization of variable so that no initialization check is missed. And when copying back an object subjected to the relaxed initialization policy to an object subjected to the regular flow analysis initialization policy, proof proves that the variable is entirely initialized. It's a design choice so that we don't have to send information to flow. Relaxed initialization is also used to annotate types. So this allows creating partially relaxed structures, and we can use type invariants or even subprogram contracts to express the initialization in a fine-grained manner. If we take an example of a stack, so we have a top field, which is a natural, representing the number of elements in the stack, and content, which is a fixed size array. And here we can see that there is no interest in initializing content components after top because they should not be accessed. So we are able to state in the predicate that all elements between 1 and top are initialized. The rest are not. When a variable of such a type is called as an actual of a parameter, the initialization of its subcomponents is not checked on calls. They are rather checked on the direct access to the relaxed subcomponent. Even though it sounds a bit weird, if we see an example, it will make more sense. So we take the stack example, we create a value x of this stack, and we try to push a value inside the stack. At the call to push, we definitely don't want an initialization check. Rather, inside the body of push, there will be initialization checks whether when the subcomponents are accessed. This will be verified thanks to the predicate. So to conclude, we finally have a complete graph. So the Spark tool performs two analyses: data flow analysis that verifies data flow contracts and simplifying assumptions. Deductive verification is used to verify contracts and runtime checks. Following the user request, the cooperation between these two analyses has become more involved. Flow, which is faster and can see the whole program, computes information for proof. Complex checks in flow are automatically deferred to proof. And for initialization, it's possible for the user to choose between the two in a fine-grained manner. So, thank you for your attention.
Thank you very much. Questions?
So how do you make all of this concurrency safe? I mean, everything you said seems to be single process or
Absolutely.
concurrent.
So we have a very coarse handling of concurrency currently. Flow analysis checks for data races, and that's basically it. Because we do not have a model of concurrency currently that will allow us to prove more precise contracts.
Maybe a follow-up to that. Yeah. I mean, just as a plug for everything we do here, I think there's been a lot of work on how do you make these, even with rendezvous communication, all of the nice things that Ada has. I think it should be doable. I mean, with the techniques that we've been looking at. So
definitely.
There's something to look at, right?
Yeah, yeah.
But very interesting.
Yes.
Just continuing on that, I guess the issue is the automation, right? Because apart from the very last bit you showed, everything is fully automated in Ada, right?
It's auto-active proof, so the user can guide the provers, because usually when the context reaches a certain size, the provers get lost and choke completely on the verification conditions. But the user is able to guide the provers using either assertions, so explicit assertions within the subprogram, or it can define lemmas and call them explicitly. But yeah, so it's automatic, but when you reach a certain program complexity, it always needs the user to guide the tool.
So maybe it's not so much of a problem for the more complex stuff if it's already requires.
Yeah.
So. Other questions? Yes.
So I guess maybe I missed something, but I was curious about whether there are some circularities in the reasoning, because you said flow, for instance, could maybe make an assumption that some part of the code is dead.
Mm-hmm.
And to get a more precise result. And then it leaves the verification of that to the prover. But maybe the prover relies on information from flow that sort of causes it to prove that that code is dead, but that's actually not true. So could something like this happen? Yes.
I don't think so in this case, because when flow makes an assumption, in this case, it's always steered by the user by adding explicit assertion, stating, I want the tool to verify that the branch is dead, and influencing the checks accordingly. But there is no, let's say, flow analysis will not create an assumption out of nowhere unless it's specifically defined and flow and proof agree on the definition of such an assumption. Okay. We have actually something related to circularities, but it's more about on the subject of recursivity, when there are dependencies in the proof related to, for example, invariance or values of constant. And for this, Flow is able to generate as well a augmented call graph to verify that this does not happen. But we do not have such a thing between the assumption made in Flow and proof. There are those soundness arguments in the paper. Basically, since Flow and proof always reason depending on what happened previously, there is no risk of trying to adding an assumption that would not be shared by the two.
Okay. Other questions? If not, I propose we thank the speaker. And I think it's time for a break until 4 o'clock.
apologies for being late, but let's get started. The very first talk is called LLOR, Automated Repair of Open MP Programs. It will be given by Utpal Bora. Go ahead. Thank you.
Thank you, Sriram. Am I audible? Okay. So I'm Utpal Bora. Today I'm going to present our work, Automated Repair of OpenMP Programs. So this work is mainly from Gautam Muruganti, but because of visa reasons, he is not able to be here. So I'll be presenting our work on his behalf. So we all know about parallel programming. If we have a big enough problem, we want to use the multi-cores that we have nowadays, and we want to break down the big problem into smaller chunks, and each smaller chunk can be processed by different processing elements. So there are different models of parallel programming. So what we have tried is like OpenMP is one of those, which is shared memory parallel programming. That means all the processing elements will be sharing a common memory, and it supports two programming models, SIMD and MIMD. In SIMD programming model, as we know, all the instructions are same. The same instruction is executed by all the processing elements, but the data is shared or mapped from the shared memory. Then for the for the MIMD model, OpenMP also supports MIMD model where you have like different set of instructions that are assigned to different processing elements, and all the processing elements will work on different data in the shared memory. So as we all know, parallel programming is good, it is beneficial, but it has its own quirks. So one thing is like one problem that we generally face with data races. So data races are a common set of bugs in parallel programming, where mostly with shared memory parallel programming, where if we have more than two threads trying to access the same memory location, and one of the accesses is a write operation, but the accesses are not protected by any locks or any order, then we might have something called data races. So in OpenMP, let's see how we can have data races. So OpenMP is a pragma directed. So so basically we provide pragmas to C, C++ or Fortran programs to define a parallel region. In this example, we have a parallel region which is defined by pragma OMP parallel construct. So all the statements inside this construct will be executed by all the threads that participate in the parallel region. So here there's a concept of shared memory and private memory. All the threads in OpenMP, they have two views of memory. One is the shared view, one is the private view. The private view, so the private variables are stored in private view of the memory, and the shared memory is basically shared among all the threads. In this example, we have like data is a shared variable, or data is a shared array that is that all the threads have access to, and we have like the other variables like temp and thread ID that are thread private. So that will not, like the data races basically occur only on the shared variables, not on the private variables. So in this example, what we can have is like, let's say there's a input array, and this array is basically the data array, and we might have like different execution sequence or execution trace of this program. So let's say we consider two threads, thread 0 and thread 1. Thread 0 has like, let's say in the sequence, thread 0 reads the element first and followed by thread 1, and thread 0 writes first and followed by thread 2. So we have the output data array after this execution. We can also have a different execution sequence where thread 1 first reads and writes to the array. Now thread 0 reads the new value of the from the array. So we have a different data, which is basically, we can have different outputs from the same segment of code. So this is basically the data arrays that we have in OpenMP programs. And there are some cases where we can have corrupt data as well, where the writes and reads happen simultaneously. If the operation is not atomic, we might have data that is corrupt. So to mitigate this, we have, so what we do is we introduce barriers. So these barriers are a construct in OpenMP basically synchronization constructs, which forces each thread that are participating in the shared region, parallel region. So what it marks is basically all the threads should wait at this barrier before they can proceed forward. So in this example, all the threads can read from the data array, but it has to wait before any thread can write to the memory location, shared memory location. So this avoids the issue that we had before. So this is how we will try to mitigate the data races in the program automatically. There is one more construct that is very popular, which is called OpenMP work sharing construct. In this example, we can see that there's a pragma OMP parallel for, which should always be followed by a for loop. So basically this pragma is on top of the for loop, which divides the iterations of the for loop among the threads, participating threads. So the statements are pretty similar to the previous example. Here also data is shared and temp and variable I is private to the threads. So we can have same issue as different outputs. So one difference between the previous one is that we cannot insert a barrier inside the OpenMP parallel for construct. So what we need to do is we use a different pragma called pragma OMP ordered. So which basically states that all the statements inside the ordered construct should be executed in the sequential order, in the program order by all the threads. So this way we can prevent any data races. So with this, let us see the goal. So the goal of our work is basically given a program which has data arrays, can we generate a program that automatically corrected program which do not have data races and which has minimal number of barriers or synchronization constructs. So this is the architecture of LLOR. We can have OpenMP programs in C, C++, and Fortran. So we use the Clang and Flang front end to generate LLVM-IR. So we compile to LLVM-IR. And LLOR has two components. The first component is instrumentation phase, and the second component is a repair phase. So the instrumentation component basically finds the OpenMP constructs in LLVM-IR, and it annotates some metadata into the IR, and it introduces some variables called barrier variables that I will discuss later. Once we instrument the IR, the repair candidate takes over. So the repair generator candidates basically reads the instrumented IR, and it queries the verifier. Here, verifier is a data risk detector, which acts as an oracle for our exercise. So in this case, we use LLOV, which is a state-of-the-art data risk detector for OpenMP programs. And LLOV reports the data races if there are any, and it reports the source location where the data race occurs. So in the next phase, what we do is we analyze the data races from the oracle, and using these data races, we form some clauses that I will discuss later. So these clauses, we send it to a solver. In this case, we use Z3 for our purpose. And if the solver says that the clauses are not satisfiable, we say that the program cannot be repaired. But if, let's say, if there's a solution exists for the clauses, what we do is we send it to the repair candidate again. The repair candidate takes the solution and enables those barriers and generates a new repair candidate, which it sends to the OpenMP verifier. Then if LLOB reports that there are no data races, we say that the program has been repaired, and we generate the source location where the barrier should be placed to fix the program. And we also generate the correct program in LLVM-IR, which can be compiled.
So you're fixing the source, not the LLVM, or both the LLVM and
we mostly fixing the IR at the IR level, but we also generate that at this source location we can put a barrier. So, yeah. So this repair candidate, these components written in .NET C#, and the first component instrumentation phase is in LLVM in C++. So together we have the tool LLOR. So this is not new to use this type of counterexample driven approach to repair programs. Like we use LLOB as a oracle, but we are not dependent on LLOB. We can use any other data race detector as verifier. Yeah, it should not be difficult to change the verifier. It should be straightforward. So let us take some examples how the algorithm works. I'll consider two examples. One is for parallel region, and the other is for work sharing for construct. So this is a parallel region where we have 4 statements. All the 4 statements will be executed by all the threads that are participating in the parallel region. And we have 4 memory accesses to the shared memory. Data A and data B are the arrays that are shared among all the threads. So the instrumentation phase will go through this in the LLVM IR. It will pick the locations where the shared memory accesses happen. So we have the 4 locations, and we instrument, we introduce Boolean variables as, we call them barrier variables. We introduce one barrier variable for each shared memory access, either it is read or write, and we send it to the repair candidate generator. Because all the Boolean variables are false, the repair candidate generator will not introduce any barriers into the program, and it will send this program to the verifier. The verifier reports that there is a data race between the statement 1 and statement 3 due to read and write to the same memory array. And so at this stage, the clause generator kicks in, where we try to read the error message from the verifier, and we read between these 2 locations, we read all the memory accesses that happen to the shared memory. In this example, there's a read access to at B2 and B3. So we say that if we place a barrier at B2, we can avoid the data race, or we can place that at B3.
So in this case, when you do the verification,
yes.
Is your verification just looking at an access into the array, or do you also look at what indices you are accessing? So in other words,
Yes.
If I change thread ID +1 to thread ID, you may not have a data race.
So the verifier does look into the array accesses. In this case, LLOB does verify the actual array accesses. So then we send this clause to the solver, which is Z3 for this case, and we can either satisfy it with B2 or B3. Let's say we pick B2, and then the repair generator candidate generates a new candidate by inserting a barrier before B2, right? And then it sends the same program to the verifier LLOB, in this case LLOB, right? So LLOB reports that there is one more bug, and at this stage, the clause generator accumulates all the clauses it has seen till at this point. So B2 or B3 was there before, and we see that there is a data race from statement 3 to statement 4, but there is a shared memory write at B3. So we add one more clause B3 or B4, because we can add a barrier before B3 or before B4. So with this, then we send it to the solver again, which solves B3, satisfied both the cases. So if we set B3 to true, that means we introduce a barrier before B3 and send it to the verifier. This time verifier detects that there are no data races. So at this point, we have repaired the program, and we correct the program in LLVM IR, but we also generate the source location where the barrier should have been put. So this is in context of parallel region. Let me take the example of work sharing for construct, where we have a for construct. It is different because we cannot put a barrier inside a for construct. So the example is very similar. We have all the barrier variables. Let's say we have the same clauses. So once we know where once we know where we should put the barrier, B3 is in the case. So what we do is, instead of putting a barrier, we put a ordered construct from the point where it should be put to the last memory access, shared memory access, or last access where it produced the data is. So since OpenMP work sharing construct only allows one such ordered clause within that body, so it might happen that we might have multiple instructions inside the ordered clause, and some of the instructions might not be accessing shared memory. So it is a limitation. But yeah, so this solves the data race issue that we have. So going into the strategies, we apply two strategies in solving finding the solution to the problem. So first one is maxset. We use maxset to solve it. Let's say we have 5 data races in the program, and let's say there are 6 memory accesses, shared memory accesses in the program. So if we have 6 accesses, we will have 6 Boolean variables or barrier variables, and we create the hard clauses based on each data race. So basically, within the data race, whatever shared elements are there or shared memory accesses are there, all those variables will be part of that particular clause. So in this case, we have 5 clauses, and the soft clauses are basically to minimize the number of such barrier variables we want to put. So yeah, the hard clauses must be satisfied. Soft clauses need not be, but we try to maximize them. The other strategy is using a minimal heating set algorithm, where this is a polynomial time greedy algorithm that we try to maximize, satisfy as many clauses as possible with minimal number of literals. Let's say with the same set of examples, like 5 clauses, if we set B2 to true, we satisfy first 3 clauses. If we set B6 to true, the next 2 are satisfied. So basically, we have a solution. So why it is useful is because maxset is costly. So we try to, because we might go for multiple iterations over generating different repair components. So instead of using maxset every time, we use MHS, and but MHS need not produce the best optimal solution. So once we have,
So you would never have a negation in any of your clauses, right?
No. Yeah.
Does that affect anything?
I'm not quite sure about it. I'm not expert in this area, so probably not, I think. But yeah, we will not have any negation. And yeah, so if once we get a solution from MHS, we send a query to maxset to find the optimal solution, and we generate the repair candidate and produce, also highlight the source location where it should be placed in the high-level code. So having said that, we did some benchmarking. We used a few OpenMP open source benchmarks. There are quite a few. Like data race bench is a popular benchmark in data race detection community, where there are multiple C++ kernels and Fortran kernels with and without data races. We know that there are some data races in these programs. And we also use some exascale projects, like these are HPC applications. These are big applications that we tried. And we also use Rodinia and parallel research kernels. And we also designed some of the smaller test cases. And for our experimentation, we used LLVM 12. And we use classic Flang, which is little bit different from, which is basically different from the current Flang that is there in LLVM. And we used the verified LLV version 0.3. So since this is the only tool that we know of that can repair OpenMP programs, we do not have any comparison with any other tool. So we categorize our results into 3 categories, basically. First one is when we have no data races in the program, or the verifier says there are no data races in the program. In that case, what we do is, like for 70, out of the 75 C++ cases, 71 are not repaired by the repair tool, but 4 of them are repaired. This can be either because of 2 things. First one is that it optimized or it reduced some of the synchronization constructs, and without those synchronization constructs, also there is no data race. And the second thing can be that, so it is that basically for a Fortran programs, there's a case where the verifier generates false negatives if we remove some of the barriers from the program. So this is to do it mainly because Flang and Clang does not generate same source code for similar programs. So I think it is an engineering issue that we have reported. So basically because of that, some of the programs are like LLOR suggests that we should repair them because that is the optimal solution without like having extra barriers. The next category is like where we actually have data races. This is the these are the ones that we care about. So out of 117 C++ programs where we have data race and the verifier reported data race, we could fix 92 of them correctly. And out of the 30 Fortran kernels, we could fix 15 of them with the strategy of inserting a barrier and putting the order clause. However, we could not repair 5 of the C++ kernels because they were not able to, like, it is not merely possible to just fix the issue with a barrier or a synchronization construct. We might need a critical section or something more complex. And there are like some cases where the program's timed out, where we set a timeout of 300 seconds. And some of the constructs are unsupported right now by LLOR because we repair only parallel construct and work sharing constructs. So there are other constructs like SIM deconstruct and GPU offloading constructs that should be fixable. Like there can be extensions to LLOR that can target those. So the last category is basically where the verifier does not support the OpenMP constructs, and there are like 43 C++ kernels and 21 Fortran kernels, either because there are complex features like Teams construct or I can't recall. So yeah, there are multiple constructs that are not supported by the verifier. Probably if we have used a different verifier, those could also be supported, and LLOR could have detected or modified the source program. And some of them had compiler issues, like 10 of them. This is because the Flang version that we used is not part of LLVM. It is classic Flang, and it is not feature complete. So some of the OpenMP pragmas were not supported in Fortran. So the recent Flang that we have in LLVM, like at the time, Flang was under development, so it could not generate LLVM IR. So it was generating ML IR and then generating like code, doing code generation directly, but there was no LLVM IR generation at that stage. So we had to use classic Flang for that. Yeah, there are plans to switch to like using the recent version of Flang, which should be able to generate LLVM IR, and some of the issues that we have should go away because these are engineering challenges. And the verification errors at last are due to timeouts from the verifier, like the verifier timed out for 6 of those cases. And yeah, with that, our tool is open source. Please go ahead and try it out. Our paper is available on arXiv, and the artifact is also available on the archival repository Jnodo. And we have received all the 3 badges from Artifact Evaluation Committee. With that, thank you for your time. Yeah. if you have any questions.
Questions?
Interesting work. I was wondering, like, did you do performance analysis of, the programs? Because you could imagine different solutions where you could put a barrier here, or you could put a barrier there, and one of them just happens to, reduce all the parallelism, and the other one keeps it. So they would both be free of data races, but clearly you would want the one that was more parallel. So
Yeah,
did you
interesting.
do those kinds of
No, and yeah, we didn't try that. Yeah, this is a very good suggestion. We should have tried that. Yeah, I think we can, optimize that a bit really.
So following up on Kedar's, so not every program, every data race is barrier fixable, right?
Yes.
You have to be able to do data race free execution in lockstep.
Yes.
That's the only case where you can introduce barriers to fix it, if I'm not mistaken.
Like not exactly that. In terms of OpenMP, let's say if we have a write operation to the same memory location, and both of them are overriding the same memory location, in that case, a barrier would not fix it. Maybe we need a we need a lock basically to protect, or we need a order clause that we shown where like the thread executes based on their ID, the lower ID threads execute first, so on and so forth. So yeah, I think we can fix some of these cases with these constructs, and there are other synchronization constructs in high-level synchronization constructs in OpenMP that I think internally uses similar locking mechanism.
Thank you. Any other questions? Oh,
I guess the question is, I can imagine a programmer could write their program in such a way that it creates a huge number of barriers, but if they had reordered their statements, it would be equally correct. Is there any sort of extension to your work that might reorder what they've written in order to get a more optimal set of barriers?
You mean like program transformation in terms of optimizing the sequence or order of the shared memory accesses? No, we have not tried that. So it was mostly in terms of verification and reducing the synchronization constructs.
So even removing existing barriers would be a good idea.
Yes.
If they put in a barrier, maybe it's not needed. You could use the same framework to remove it. That would be great.
Yes, precisely.
Thank you. No other questions? Let's thank the speaker.
Thank you.
Okay, so the next talk, while the speaker sets up, is going to be on the synthesis of locally symmetric protocols from abstract temporal specifications. It's going to be given by Ruoxi Zhang.
Hi. Oh, great. Hi, my name is Ruoxi, and I'm here to present the paper, Synthesis of Parametric Locally Symmetric Protocols from Abstract Temporal Specifications. This is a joint work with Richard and Kedar. So first, we will start with an overview of the problem and our approach. So this work falls into the category of temporal synthesis, which is a problem of automatically constructing systems from their correctness specifications. More specifically, the realization problem finds processes that jointly satisfy the system-level specification phi against all possible inputs. The realization problem for distributed system is generally undecidable, and the cost to construct distributed systems by computing the product machine is exponential in the length of the global specification. So our goal is to synthesize parametric protocols from temporal specifications. Examples of parametric protocols include network communication protocols, distributed algorithms, and multi-core hardware models. So the protocols we focus on are locally symmetric and composed of k-isomorphic copies of a representative process Pn. So here, one parameter we have is big K, which is the size of the network, the number of processes that we have. So we use Pn to denote the representative process, which is a generic process, and Pn interacts with its neighbors. Here is our second parameter, lower k, which is the number of neighbors of Pn. We will use the Denning philosopher protocol on hypercubes as our running example. So in this paper, we introduce a semi-automated approach. So in the first step, given a global specification phi, we reduce it to a local specification phi n that describes the behavior of the representative process Pn. So the local specification is independent of the size of the network, but is still parameterized by the number of neighbors. So then we rewrite the local specification by a counting abstraction to remove its dependence on lower k. Both step 1 and 2 are done by hand and can be automated to some extent, which is considered future work. And then we automatically synthesize an abstract model from the abstract local specification, such that any abstract representative process extracted from the model should be able to be instantiated to form system instances that satisfy the global specification for arbitrarily large big K and small k. So we will use the Denning philosopher protocol to illustrate our approach. So first, globally at the system level, the global specification describes the behavior of all component processes. So in this particular example, big K increases with small k, and the big K is 2 to the power of small k. In each system instance, here we list 3 of them here. In each system instance, both Ks are fixed. And then when we reduce the specification from global to local, we describe the concrete behavior of the representative process. When the number of neighbors, which is small k, changes, the concrete behavior is different. Lastly, when we using counting abstraction to abstract the representative process, we will have a single abstract representative process. And that can take on any configuration of small k and be instantiated for any big K. Then we have some formal definition to describe the computational model. We are interested in protocols that formed by replicas of the same parametric tiling pattern. So the tiling pattern specifies the internal variables of the representative n and the shared variables shared with each neighbor m of n. So in the particular running example, n has 3 internal variables, thinking, hungry, and eating, and n shares with each neighbor m 3 external variables, fork nm, token nm, and dirty nm. When we try, given an underlying network, when we try to construct the system instance, we replicate the tiling process and instantiate it at the nodes of the underlying network. So let's use the particular blue edge, for example. In the Denning philosopher protocol, fnm has the negation value of fmn because they refer to the same fork, and the fork is owned by one of the adjacent processes. And the same goes for the token, but for the dirty and clean status, DNM is equivalent to DMN because they refer to the same fork. So here we formally define the representative process as a set of states, a set of initial state, the transition function, and the transition relation, and a labeling function. Here, a local state of n is labeled by the internal and shared variables. And then for each neighbor m, a joint state is a pair of local state, Sn from Pn and Tm from Pm. The two local states must have the same value for all shared variables between n and m. And here is an example joint state. So in the joint state, Pn is hungry, Pm is thinking, and the fork is owned by Pm, the token is owned by Pn, and the fork is dirty. The state transition system of n is denoted by Hn star, and it has two types of transitions. One is from a local state of n to another local state of n by the process n itself. For example, the transition from thinking to hungry falls into this category. And then interference transitions from a joint state to another by a neighbor m. For example, if Pm is hungry and sends the token to Pn to request an unowned fork, this transition interferes with the local state space of Pn by changing the variable Tn from negative to positive. And we use dashed lines for all the interference transitions. Then we start to introduce our the main approach of our paper is the specification rewriting transformation. Given the parametric local property phi n that describes the behavior of Pn in the unbounded neighborhood, we are trying to abstract the specification into something that's not dependent on the number of neighbors of n. We use FAIR-CTL as the specification language, and FAIR-CTL makes sure that the path quantifiers for all and exist are performed only on unconditionally fair paths. And since we are only focused on the behavior of n, we use indexed next time properties instead of the traditional next time properties. And we allow FAIR-CTL properties to be parameterized over n. Parameterized over k. So the first example shows that if we have a property says for every m along all the passes globally, the precondition is true, which says the process Pn is hungry without the fork, but with the token, then along all the next time transitions by n, the post condition is true, which says Pn sends the token to Pm to request the fork. We also allow the FAIR-CTL property itself not be parameterized over the neighbor, but contains terms that are parameterized by the neighbors. So for example, when Pn is in eating with all the forks, and all the forks are clean, Pn in all the next times by n, Pn send the Pn dirty all the forks. One limitation of our method is that the eventualities parameterized over the neighbors are not allowed. So the overall goal of the specification rewriting transformation is to rewrite the parametric local property phi n into an abstract local property phi na, and such that the abstract property should be independent of the number of neighbors. We use an accounting abstraction to do that. We start with two variables to estimate the number of neighbors with a particular shared value, one for accidental and one for universal. And then we write the parametric property into abstract property using the abstract domain. Also, we want to making sure that the abstract local property preserves the realizability. That means if we have some satisfiable abstract model, then it is guaranteed that it can be concretized into concrete models that satisfy the concrete local property. So here is one example. This is our running example from the Denning philosopher protocol. It's about requesting the unowned fork from the neighbor. And given an abstract precondition that says Pn is hungry, has some forks, has some but not all forks, has some but not all tokens. We want to write an abstract property with this abstract precondition. We identify that there are multiple ways to satisfy the abstract precondition. Here we list two of them. The first one says for some neighbors, Pn has the token but not the fork, and for the rest of the neighbors, Pn has the fork but not the token. And in the second case, for some neighbors, Pn has the fork and the token, and for the rest of the neighbors, Pn does not have the fork and does not have the token. So in each of the way, we compute the abstract post condition by applying the parametric update in the parametric property. And in the first way, we know the abstract precondition changes into beta NA, which is Pn since all the tokens. And in the second way, alpha NA remains unchanged. Since we have two post conditions, we put these two abstract post conditions into an abstract property. Here, there exists one transition by n that remains unchanged, and exists a transition by n that changes to beta NA. And the other two transitions are true for all the n transitions. So we describe the detailed procedure for specification rewriting in the paper. Here we just give a brief summary. Given any parametric property with a precondition alpha nm, a universal post condition beta nm, and a set of parametric existential post conditions, we calculate the set of abstract preconditions, that is the over approximation of the parametric precondition. And for each of the abstract precondition, we write an abstract property by doing a case split. So in the first case, the abstract precondition is exact, and in the second case, the abstract precondition is an over approximation of the parametric precondition. In both cases, the abstract post conditions are calculated by applying the update in the parametric property. But in the second case, just as shown in our running example, when we have different ways to satisfy the abstract precondition, for each of the way, we compute the abstract post conditions separately. Because the indices of the processes are omitted in the counting abstraction, so we introduce context as auxiliary information to represent the concrete changes in the abstract transitions. So the context defines a subset of the over-approximated state set, and the parametric update in the parametric property only applies to this subset. And we use context to concretize the abstract model we have. So on the top right is the abstract structure created from the abstract property, and given a concrete state that shows Pn has two neighbors. The first neighbor 1 has the fork shared between n and 1, and Pn has the token shared between n and 1. Then this neighbor satisfy the parametric precondition in the context. So it applies the parametric update and get into the concrete post condition. And the concrete structure is guaranteed to satisfy the concrete property with lower k equals to 2. So the overall soundness theorem states that if an abstract model is synthesized from the abstract local specification, then for any number of neighbors, a concrete system derived from the abstract system by concretization satisfies the concrete specification. Then we can instantiate the abstract process with different number of neighbors and different number of processes in the network to form any system instance that satisfies the global specification. And the cost for instantiation is linear in the size of the network. So we avoid the exponential blowup in the size of the network and the size of the neighborhood. So now the only missing piece is the tableau construction. So like how we automatically synthesize an abstract model from the abstract local specification. We modified the existing iterative tableau-based decision procedure for CTL. So in our modified decision procedure, we first construct the initial tableau from the abstract input specification, and then we construct the next time tableau from the current tableau by traverse the current tableau for transitions that make changes to the shared variable and compute the isomorphic changes and apply interference transitions by the neighbors to the current tableau of n. And we repeat step number 2 until the tableau reaches a fixed point. That means there is no more nodes and edges to be added to the tableau. At that point, we have a fixed point tableau, and we apply deletion rules to remove inconsistencies from the fixed point tableau. If the root is not deleted, then we can extract a model from it. The representative process is just the model removing all the interference transitions by the neighbor. So the key of the construction is to add interference transitions based on existing isomorphic transitions by n itself. So in our running example, we have Pn request send the token to PM to request an unowned fork. So we take the isomorphic transition. That means a neighbor PM, when PM is in Hungary and Pn has the fork, Pn has the fork and PM has the token, PM can send the token to request the fork. So that means in the state space of Pn, if Pn has some but not has at least one fork, but not all the tokens, then eventually the interference transition happens because PM sent the token to request the fork. And also the context is isomorphic to the context of the transition by n. In the paper, we proved that the constructed system HNA, which is abstract local model, satisfies the abstract local specification VNA. And the model is closed under neighboring interference and unravels into an abstract representative process, PNA. And the worst case cost of synthesizing the abstract representative process is exponential in the length of the abstract local specification, so independent of both cases. So for applications, besides the Dunning philosophy protocols on hybrid cubes, we also included another application for atomic snapshot protocol on fully connected networks. And the atomic snapshots algorithm implement the snapshot operation that returns the simultaneous state of all the processes. And here is the model, the local model for the atomic snapshot algorithm. If we remove all the dashed transitions, then we have the local, single representative process PNA. In conclusion, our paper reduced the global synthesis problem to the problem of synthesizing a local abstract representative process. So we first write a local abstract specification, VNA by hand, and then we synthesize from this specification an abstract representative process. And the abstract representative process can be deployed at the node of underlying networks to form instances of arbitrary size and configurations. So for future work, we plan to extend our work to synthesize protocols for which counting abstraction may not be sufficient. So we plan to extend our work by using a more general abstract domains. And also our approach focus on a single representative process. And we want to extend our work to be able to work with systems with multiple equivalent classes, so multiple Italian patterns and multiple representative processes. So for example, the red-black protocols, consumer producer protocols, for example. And also, we want to apply our work to work with fault-tolerant systems. So that concludes my presentation. Thank you.
So, questions?
Sorry.
Okay, so maybe I have a question. So you are using counting abstractions, and if I remember right, that's just counting the number of neighbors of a process that satisfies a certain predicate, right? That's how you're using it.
Yeah.
So what more would you need? I mean, why is that not enough, or what are the limitations of using a counting abstraction?
I think, for example, we are focusing on Boolean variables. So maybe if we want to handle protocols that has integer values, then we need other abstraction instead of only counting abstraction. Yeah, there are like many other protocols that requires other kinds of abstraction. Yeah.
Any other questions? So if not, let's thank the speaker again. Last but least not the least talk of VMCAI is going to be by Julian Erhard, who is going to be telling us about how he likes to bridge the semantic divide with ghosts.
Can you speak again?
Yes, hello? Yeah, okay. Good. So then we can come to the definition of witness validity with respect to semantics. So we say that a witness for a given program is valid with respect to semantics if and only if the witness instrumented program is safe with respect to the semantics. So that means the witness is valid if the original program is safe, so all the assertions in the original program do hold, and also every additional assertion that is introduced by the witness also holds. Now we stated some theorem that the local trace semantics and the interleaving semantics are actually equivalent with respect to safety. So that means that every program that is safe with respect to the interleaving semantics is also safe with respect to the local trace semantics. And so that required some proof engineering, which I will not go into very high detail. But what we basically had to do was to define a class of traces, which were not quite local traces, for which we could construct interleavings and vice versa. And then we showed that for every local trace, we can extend it to one element of this class of traces, so that basically whenever we have a local trace that violates an assertion, we can obtain an interleaving that violates an assertion, and vice versa. So based on this notion that the safety coincides for these two different semantics, and based on the definition of witness validity, which is based also on safety, we can now make the claim that a witness is valid with respect to the interleaving semantics exactly if it is valid with respect to the local trace semantics. And so this is the core theoretical outcome. That basically means that this ghost witness format makes sense or yields the same result whether you view it from the local trace point of view or whether you view it from an interleaving point of view. So, and besides these theoretical results, we also have introduced a format which extends an existing format for software verification witnesses, this witness 2.0 format, which is also recently now used in the software verification competition as VComp. And here you can see an example of how one would specify that there's some ghost variable and that this is updated at some specific location. So this is it with respect to the format. So now we come to the evaluation. So we implemented something in two tools, namely in Goblin, which is an abstract interpreter. We implemented a means to generate ghost witnesses. And in Ultimate Gem Cutter, which is a model checker, we implemented a means to validate or check witnesses. And we performed the experiments on the concurrency safety main category of SVComp, which contains several hundred tasks. So what witnesses did we look at? So we equipped Goblin, so two different analyses that are implemented in Goblin with means to generate ghost witnesses from their results. And so one of these analyses we call protection-based, and the other one we call mutex-meet. And both of these analyses are actually justified with respect to proofs based on local traces. So our first research question was, can witnesses that are generated by Goblin so by one tool, can they be confirmed by some other tool? And indeed, we found that most of the witnesses could be confirmed. So for the one analysis, for this protection analysis, we generated 181 witnesses for correct programs. And most of them could be confirmed by ultimate. So that is all of the claims that were made by the witness do hold according to ultimate. And then also for the other analysis, we generated 217 witnesses, and most of them, again, could be confirmed by ultimate. And we did not only look at the correct programs, so to have a broader set, we also looked at the incorrect programs. But again, ultimate here only had to verify that all the claims made by the witness created by Goblin do actually hold. And here, again, most of the witnesses could be confirmed. Now, the question with respect to performance. So sometimes witness validation can actually speed up the run of the validator compared to the validator just verifying the property on its own. But sometimes it does not speed up, and sometimes it becomes slower. So what is the case here? So in our experiments, when ultimate had to validate the witness, all these witnesses for the protection analysis, there was, so this is the overall runtime in hours, so there was some slowdown compared to just verifying the property on its own. And so this also holds similarly for the mutex meet analysis. So there is some slowdown, but it's not too bad. And there was even one case, so for one witness, ultimate was faster in validating the witness than verifying the property on its own. So now another key question is, can this witness format actually help us with increasing the quality of static analysis tools? So because one of the reasons why we actually want to have witnesses is to increase the trust in the verdicts that these tools make about programs. So and actually, during the development of this format, we found quite some bugs in both Ultimate and Goblin, in total 29. And so there were some examples where Goblin previously computed unsound information, actually. So because of some errors in the domain, or because some analysis did not treat some variables correctly. So there were even unsoundnesses that we observed because of these, because of the witness, and that we found out because of the witness. And then on the other hand, for Ultimate, which was the tool that validated the witnesses, we also found that some code that was already doing, so that for the validation contained some mistakes that were actually already present for the witness validation without ghosts, but this bug was not recognized previously. So, but these are just some examples of the bugs that we found. So to summarize, we have bridged the semantic divide between the interleavings and local trace semantics by using programs as the ground truth, building on this on the ghost instrumentation, and provided a machine-readable format that can be exchanged between tools, and that facilitates the exchange of information, and already was shown to help find bugs in static analysis tools. So that's it, and so I'm happy to take your questions.
Yes, thank you for the talk. I have a whole list of questions, but I'll start with one, and we'll see. Yes, so I was a bit confused by your translation of this kind of English language statement you wanted to verify about like when the mutex is not locked, something is used or something, into the formalism, where you, if I understood correctly, asserted this invariant at a single line, whereas if it's an invariant, it should hold everywhere, right?
Well,
so
I mean,
that's a bit confusing.
Okay, so yes, so I mean there are different notions of invariant. So one thing is you can still specify an invariant that holds at some specific location. So then it's like a location invariant, what we would say. And you are right that one would also like to be able to specify that something holds globally, right, at every program location. That is also something that one would like to have, but we currently did not have this in the proposed format.
But the English language version you had was whenever. But
yes,
like what you actually formalize is at the beginning, like after the first line of the program.
Yeah, so I mean, the thing is that you can still express with this is that it does, I mean, the other thread is you don't know, so if you don't have the ghost, you cannot really specify where is the other thread, what is the other thread doing. And now with these ghost variables, you can specify whether the other thread is in a critical section or not, or whether any thread is in a critical section or not. And so that is what these ghost variables.
Yeah, the ghost variables are clear.
Yeah,
it's the placement of the invariant.
Like,
yeah. I mean, I would have expected at least something like just saying this at every single line or something like that.
Yes, I mean, one could introduce that, but that is currently also a limitation of the existing format that you have to specify it by line. So one could introduce it, but currently we do not have that.
Okay. Okay. Thanks.
Yeah. Maybe other questions, Kedar, and then we can do the ping pong.
Yeah. Thanks. That was really interesting. So I was sort of maybe going to build on this previous question. Is that so? Based on your explanation, like with interleavings and local traces. I was starting to think of this as a modular verification method. So you also introduced Ovicki and Grease's work, which is, the reason they have ghost variables is because they want to construct compositional or modular invariants. So you have, and just what you were explaining, that the ghost variables kind of tell one process what the other process is doing, right? So first of all, is that true? Is that how you're thinking about these ghost variables and the invariants that you write with them?
Yes, so I mean these ghost variables are, I guess, in general quite powerful. But yes, I mean the main idea is that with the state of the ghost variable, you can basically encode some information about the progress of multiple threads, and yeah, thus you can really in your C expressions or in your assertions you can then use this information.
Yeah. So then the other question was with your experimental results. So is the verifier actually checking these invariants modularly, like one process at a time? In which case it should be really fast, or is it building the entire state space? I mean, I was surprised that the verifier was taking so long, and that in some cases it was almost the same time as the actual analysis, right? If I got
yeah, I mean, so actually it was even slower than so it had, because, I mean, the reason for that is because it basically had to construct this ghost instrumented program, right? And so there was more code to analyze and also more assertions to prove. So this means that there were more proof obligations. And well, yes, so with respect to how does the verifier work? So this is this ultimate gem cutter. So it's a model checker that does some commutativity reasoning behind the scenes. So it tries to reduce the overhead of the analysis of concurrent code, but I mean there's still some scalability problems. So that yeah.
So just to sort of suggest that you need a different verification strategy instead of just giving it to any model checker, because now you have these ghost variables. You should be able to just check the code or the invariance of each process independently of the others. I mean, that's what my intuition says.
Yeah.
So you should just be able to analyze one process at a time, verify it very quickly.
Yeah. I mean, that ideally that would be the case. The thing is, with these witnesses, it's always a question on how much information is actually expressed in the witness, and does the information that is expressed in the witness, does it suffice to show the property that holds? And because sometimes the properties are quite intricate, and this is sometimes hard, and there are even some technical limitations that the witness, currently also our witnesses, are not able to express everything, because, for example, arguing about things that could be pointed to and so on is a bit hard in this format still.
I think I tend to agree that it's a bit odd to have a witness which is hard to check. Like, the point of a witness seems to be that it's easy to check. But anyway, actually going on this pointed to that you just mentioned, so a common approach to verifying concurrent programs is separation logic. So do you have any thoughts on how one would take a separation logic proof and turn that into your witness format? Or what would have to be added to make that possible?
So for separation logic, I could not, at the top of my head, answer this, no.
Okay, fair, thanks.
All right. Oh, it's 5:30. Yes, please take it offline. So your talk is introducing a lot of questions, so please stay offline, take it. Thank you everyone for attending VMCAI 2025, and we had a great set of talks. Let's thank all the speakers and all that.